Hello everyone and welcome to Handmade Heroes, show where we code a complete game live on Twitch. No engines, no libraries. And right now we're doing some optimization work. This is the first time we've done optimization work on Handmade Hero. It's gone really well. The stream was yesterday. On the schedule. It's the first time we've ever done a Thursday stream and then a Saturday stream here today. But that's because I was speaking at a conference yesterday. A lot of people, so I didn't want to do two public things in a row because your voice, you only got so much voice. It was already pretty hard on my voice doing the speaking thing because I did a rehearsal and then the regular and yeah. Anyway, long story. But point being, a lot of people have asked where they can see the lecture, if it was recorded, etc., etc. It was recorded. The AV people looked pretty professional actually. For a small conference like this, they actually looked like they were some pretty serious AV people. So it will be available at some point, but I don't have a firm date for when they will get all of the video processed and up. But just as soon as it is, I will mention it on the start of the stream here, and I will also post a link to the Twitter feed. So this guy right here, he will have a post of it when it is ready. So I'll let you know as soon as I know, but I don't know anything yet. All right, let's get to it. Today is day 121. If you would like to follow along with the source code, you can unzip day 120 source code, because that is the source code that I am starting with right now. So one of the things that was tough on Thursday was that we tried a new tool that Fabian had sent over that allows us to analyze the use of the processor, of the Nehalem processor that's in this machine. It allows us to analyze the use of the processor on the code that we wrote. And it's like a much more complete version of what I thought we might have to build ourselves, because I was like, well, I showed on I think Wednesday stream how to use intrinsics to kind of go in and how to use pound defiance to count your intrinsics. They basically did a thing that kind of is cooler, where they would inject into the executable markers that they could grab, and then they would just read the source code out from the actual executable, and it would be able to do analysis on it there, which is also pretty cool. And honestly, we didn't really go over this too much. I'll kind of point it out again. It's not super relevant to what we happen to be doing right now, but it was kind of interesting to me, just in general. I didn't really know about this. So anyway, I just wanted to point it out. The way they were doing that was with a thing that I didn't know you could do in the compiler. So if you remember, you put these like IACA, VC64 start and ends. You put those around the part that you wanted to have it analyze. And then if you include, let's see, IACA 164, IACA marks, you just have to include these little markers. And what it would do on the 64-bit compiler was this thing right here. So I didn't know you could do this, write GS byte. And what's kind of neat, I just want to point out what this does, because it was kind of news to me, and it's something that I might play with in the future because it's kind of cool. But basically, what this does is it actually writes like a known piece of information, basically, right? It writes whatever this thing is in here. You can see what it's writing, right? It's actually doing a write of a particular piece of information. It's inserting that directly into the program, I guess might be a way to say it. So I want to just show here kind of roughly what this does and how this works, because it's just kind of interesting. And today, since it's a Saturday, I don't have a schedule. We could stream all night if we want to. So if we want to spend a bunch of time going on tangents or doing whatever we want, as long as we do an hour of actual programming on the actual game, we can do whatever else we want, and it's not really a big deal. So I don't feel super time constrained. So if I go in here and I turn this on, right? Let's go ahead and do that. If I turn that on, and then I go ahead and launch our game, and I'm going to do draw rectangle quickly. That. When we get here, what we should see, and you know what, also too, just to make it easier to find, you know what I should do is go ahead and turn off optimizations in the compiler so that our code will be more straightforward and more similar to the actual code that we have. So here we go. And let's see. Here is that code. Let's run to it. And I'm going to right-click here and click Go to Disassembly so that we can see what's going on, right? So now what I assume, and I could be very wrong about this, but what I assume they have done here, and you can see, this code, right? This 6FH, right? 6FH, or O6F, right, as we know it, is that 1111. And you can kind of see that's what they had passed in that marker, right? 1111, 2222. So what they've done here is they've inserted a thing that I believe their idea is that this is a thing that's very unlikely for the compiler to ever have produced for any reason on its own. A write to the GS segment thing, a write to that location is not something the compiler will ever produce, right? And so it's not that it actually needs a write to go to that location. It's that it just needs an instruction it knows that the compiler will never put in the command stream, so that when you tell it to analyze something, it can just scan the executable for this. It's going to look for that, right? It's basically just going to grep the, oh, sorry, not that. It's going to look for, there we go. This is the address where, this is the actual location of the executable. Oops, sorry. This is the actual location of the executable. It's going to look for this, right? It's going to look for the byte code that's saying, well, byte code's probably the wrong word. It's going to look for the encoded instruction that does this operation because it knows the compiler had to insert that and would never probably insert it for any other reason. And then they do the same thing for ends. They just use a slightly different value. So then it can scan from there through the executable until it gets to the corresponding, where are you? Come to me. There we go. Till it gets to the corresponding write to the GS segment, right? And it's basically got, it's almost like, you can think of it like DNA markup, right? It's almost like inserting these markers into the code that it can use to look and see where it is you want it to analyze. Now, the reason that I point this out is because if you, again, one of the things we try to do on the stream is encourage sort of these advanced programming practices of like, hey, I just want to kind of expose everyone who may not have had the opportunity to see some of these things before in their programming. I just want to point out when we see these things that are kind of advanced programming tricks, that's a pretty interesting one. In fact, it's one I didn't really even know about. It's the kind of thing you used to do with the inline assembler, but they removed the inline assembler in the x64 compiler, and I never really thought about how you might get that trick back, but now it's back. This is a pretty cool way to do it. And so what this means is you can mark up the code using this write.gs byte thing, and then if you have an external tool that wants to grab chunks of the actual code that came out for whatever reason, analysis or moving code chunks around, hot loading them, I mean, who knows what you might want to do with it, right? But whatever you might want to do, this allows you to insert those markers in there in a way that an external tool can trivially sweep through and find without having to know anything else about that executable, right? It doesn't need to know like how to read Microsoft's PDB file or how to read a map file or anything else that the compiler might speed out. It doesn't need to know how to read some other markup to figure out where the code is. It can just use this. And so I think that's a pretty cool trick, and I just wanted to highlight it. That's how that's working. Okay. So let's clean up another thing from the other day, which is that I had to try and figure out how to use that tool on the stream, which was way too hard for me. I'll be honest, it's very difficult. I've said this multiple times, but it's very, very difficult to talk while you are programming. And the only real reason that I'm able to do it is because I've programmed for so long and because I talk way too much in my normal everyday life. So it's like I've had so much practice at both those things that I can make it work. But when I'm faced with something that I've never seen before, ever, it's really hard for me to integrate. So I had a really hard time parsing that thing, and I needed a little bit of time to like spend on it on my own so I could understand how to use the tool. And so now I can give a much better explanation of how it works for anyone who maybe didn't get it. I suspect most people did, because I feel like when you're able to look at it on the stream and you don't have to talk, it probably sunk in a little bit better. But just in case it didn't, I want to now say, now that I know how it works, I want to explain a little bit better about how it works, because I was not able to do that because I didn't know how it worked, right? And so now I kind of do. All right. So the first thing I want to say is I want to explain what my confusion was about the tool first, because I think that's also potentially kind of interesting. So I don't know if you guys remember this, but a long time ago, I'm trying to remember where this actually was. Where is this going to be? I don't know, but I think it's probably in here somewhere. Where do I find it? Where indeed? Let's search for it by name and hope we find it. I don't know if we will. I don't even know if it's on this machine anymore. But we will know when the little searcher thing, if the little searcher thing actually completes, we'll be able to find it. I actually showed it before, so I know it at least used to be on this machine. What I don't know is if I deleted it off this machine at some point. And this machine is a totally old, non-used machine anymore, so I don't actually know. I don't actually remember exactly what's on it yet. I feel like it should have been on. I feel like it should have been on here somewhere, but I'm not seeing it, which makes me a little bit, yeah, that's not going to be where it is. Yeah, I don't even remember where things are on this machine. So it doesn't look like it is, which is weird because it was. I wonder if it just got deleted at some point. Look at it. Look at it going towards the end there. Why is this little part taking so long? Come on. Come on. You can get there. But it looks like it's not there, so unfortunately, maybe it's in temp? Oh, it's in temp. There it is. Now, people asked me if this was because I was mad at Jonathan Blow. We showed this on the stream once before. It was like on the desktop or something. And no, it's not. I don't think I've ever been mad at Jonathan Blow. For some reason, words just pop in my head sometimes. And I think I was combining like blowhard with retard or something. And I was mad at something like a dev kit. And so I typed that in, I think. That's just how that works sometimes. So anyway, I'm going to go ahead and show this here. So this is the output of a tool that I wrote. It was a compiler, and what it was a compiler that was designed to make blit code for the Xbox 360 of various kinds. Blit code is probably the wrong word, but operations. It was designed to generate 360 stuff. And so the way the PowerPC works, this processor is fairly documented at this point, so I'm not really violating any NDAs by explaining some of this, because they've actually reverse engineered it all. I checked. On the Xbox 360, you had a processor that could issue, if I remember correctly, and again, like I said, it might be a little hazy of exact, I can't remember a lot of the exact specifics, but basically what happened on that processor was that you could issue 2 instructions every cycle, but you could only issue those 2 instructions every cycle if nothing none of the resources that they needed were blocked. It's kind of similar to any processor like we've been talking about with units, right? And so, the processor has units, and if those units are available, you could issue it. So Unlike the processor that we're working on now, the Xbox 360 was an in-order processor, which means that as you go through the instruction stream, the only instructions that it can execute are the instructions that come immediately after the ones that just got executed. So when it comes in here and you see something like add I, which I think refers to add immediate. So it means take the register 18 and the register 0, right? I don't remember the ordering for these things, if it's R18 to R0. Oh, well, but R0 is just going to be 0, right? So I suspect it's probably R18 is the register for the destination, and R0 is the register for the source. That's my guess. Different assembly notations have different conventions for whether the destination register comes first or second. But looking at this, I believe R0 on these RISC processors, on the PowerPC processors, R0 isn't really a register. It's just a constant value 0 you can use. I don't remember if that's true. Like I said, I don't remember a lot of things about this, but basically that's the thing I'm using to determine that it probably is source register here, because you can't write to R0, would be my guess. In fact, we could sort of do a quick spot check and see that R0 is never written to, but of course it's not writing to some other registers too. But so anyway, it would come in here and do something like, let's say we start on this line of execution. Then what would happen is it would be able to issue these two instructions potentially. So it would be able to issue add I, so it would add 0 and 16 to and put it in 18 in register 18, and that's an actual immediate 16, the value 16. And then it would try to issue add R3 and R5, those two registers together, and put it in R27. Okay, that's just what it would try to do. And those are the only two instructions that the processor can attempt to execute at that time. So literally, it does not matter if there's anything else in here that it could be executing. It can only try to execute these two. So it will definitely execute the first one, we assume, because we don't have anything, we're not considering the code above it, so it's going to execute this one. And then it will try to execute this one on the same clock cycle if it can. Now what you can see from the output of my tool here, which generates both the code and markup of the code, it's how I wish compilers normally worked, right? I wish compilers normally outputted the code and markup of the code so that you could see what it at least believed would be the problems on the chip. Unfortunately, they don't do that. But that's what I want, so when I wrote the thing, that's what I did. So what it does here is it's telling you, right, down the side, it's basically telling you what it thinks the execution clock is going to be. So it's saying, I'm going to execute this on clock 0, I'm going to execute this on clock 1, I'm going to execute this on clock 5. And what you can see here is this thing over here tells you the reason why it is not able to execute this instruction and how many cycles it was delayed for. So it basically says, okay, you know, I can't execute this add on cycle 0, which is where I would have been able to execute it normally, because I know the processor can execute 2 things at a time, because the pipeline for the add is full. There's only one add pipeline, I think, on the 360, which means that once this add went into it, the second add cannot go into it. So it has to wait one cycle for the first add to finish. Does that make sense? Not to finish, sorry. For the first add to move out of that stage of the pipeline. Because remember, on a processor, things can be staged in pipelines, so the adding unit, right, is probably pipelined, which means that things move through it in a couple stages on a couple cycles. So maybe you could have many adds in flight at a time, but you may only be able to issue one add at a time into the front of the pipeline because there's only one slot for an add in every stage, right? So it goes into the pipeline, the first one goes in, and on the same cycle, you can't put another one in. But on the next cycle, you could, for example, right? So that's what this is saying. It's saying the pipeline was full. I need to wait one cycle to get another add in there. So it does. And then on execution clock 1, it'll put it in there. Then it's followed by yet another add, right? And so that other add now gets delayed for much longer, as you can see, right? It says that it can't execute that until clock 5. It says that there would have been a pipeline stall of one cycle, because again, when it got here and waited a cycle to issue this, if this were not another add, it could have issued this right away on the same cycle, EX1. Because if this were something other than an add that could go in a separate pipeline, it wouldn't have to wait for the pipeline. So it's like, I got to wait one up for the pipeline. But it turns out that that's not the worst thing. The worst thing is it actually also has to wait for R27 to become free, which is an additional 3 cycles, right? So you can, and the reason you can see is that R27 was used here, and then it immediately gets used again. Does that make sense? So it has to wait for R27 to be for the result of this add before it can issue this add. Does this make sense? And you can see as we go down here, right, the compiler did a pretty good job. In fact, this I think was a pretty good routine as far as things go. There's very few stalls in it. If you take a look at this routine, you can see that most of the time it got perfect pairing. So most of the time it was dual issuing, right? If you don't see anything over here besides the execution cycle, that means it got a dual issue on it, right? And you can see dual issue, dual issue, dual issues, right? All over the place. So it was pretty good. But this is what I was used to thinking about because that's the last time I did one of these things. And like I said, this is why I say I was much better at Xbox 360, understanding how to do optimization on that, because, you know, I actually wrote a compiler that could do all this, you know, a bunch of stuff on it, and I actually had it down to thinking about exactly how to schedule each individual instruction, and to do that I had to know all about exactly how the processor worked and all that sort of stuff, right? So that's what I was thinking about, which is why, you know, like I said on stream too, it was difficult for me to figure out what was going on with the tool, because the tool is nothing like that. And I thought I was sort of looking at a readout that was like what my thing produced. That is not what this is. And there's a good reason for that, and we'll talk about that in a second. So let me go ahead and bring up what the tool does, right? So it's a 64-bit input file. Obviously, we want to look at Nehalem, which is the processor architecture that we happen to be on at the moment. I think that's it. That's all I need to set. So let's go ahead and grab that file. Doesn't really matter which one I guess we look at, but here we go. Oh, wait, that's not what I want to look at. I want build handmade.dll. Invalid arch. I guess it has to be capitalized. Okay. So why are you having trouble? There we go. Guess it has to be an optimized build? That's weird. Right. Oh well, doesn't matter. Anyway, point being, so here we go. What I thought I was seeing here, right, was something, what I thought this would be showing was something similar to what I was looking at. So I was expecting these things to be something about the way the processor would execute stuff. But that's not what this shows. So what this actually shows is it really has nothing to do with order at all. The only thing, this is just a straight table. It's not an actual step-by-step readout like what my tool produced. What this is it's just telling you, okay, this instruction cost this many micro-ops in this slot. That's it. It's just a table. And that was the majority of my confusion. So literally all this table is showing you is it's saying if you want to know for any particular one of these instructions, if you want to know what micro-ops it generates on which ports of the processor, right? And ports are basically like those units where you're putting things into the units, right? If you want to know how many micro-ops go into how many to which ports on an instruction, this tells you, and that's it. So the reason that this is like that and does not look like something like my tool, because something like my tool is what you need. That I think the way my tool works is exactly what you want for a processor like the 360's processor. The reason that they do it this way is because the x64 is a highly out of order processor. It has a giant micro-op window. I think someone on the stream posted 196 micro-ops or something like this. I don't know if that's correct, but either way, I think I remember it being something like 40 micro-ops on the original P6 or something like that. And that was 10 years ago or something. So I could believe that it was up to 190 something micro-ops now. Right? So that's plausible. So basically, because it's so highly out of order, what the processor is really doing is it's looking at, basically 2 pages of this roughly, or some even more really, like a couple pages of this. In fact, this whole thing may fit in the micro-op window, right? I don't know how many lines is this. Total number of nodes 284. So basically, half of this loop, over half, like 2/3 of this loop, fit in the micro-op window, which means that it can execute any of these things as long as they're not serially dependent on each other. It could pick any of them at a given time. So showing a step-by-step thing would be kind of impossible because it's like, we don't know which one the processor is going to pick next. It could be tons of these. So instead, what they try to give you to help you optimize is just an idea of what port will be the most heavily utilized, first of all. And we can see that right now in this particular one, it's port 1, right, 97. And in fact, it lists that for us here. And the reason that is an interesting number is because we know that even if the processor did a 100% perfect job and there were 0 serial dependencies, meaning you could execute any of the commands at any time, you would still only be able to go 97 cycles. That would be the fastest you could go, would be 97 cycles, because we know that the processor cannot issue 2 instructions to a single port in a single cycle. So basically that is it. It's like you have 97 of these things that have to go to this port. That means you will require 97 cycles, right? Now it may take a lot longer than that depending on other aspects of the processing, but you absolutely will take 97 cycles at a minimum. And so that's the single most important number. And then the second most important thing is this critical path thing here, which I haven't really played around with too much. But I believe all the critical path thing is actually showing, because there's 2 things that I kind of thought about for critical path that it might be showing. But when I looked at it, I was like, oh, okay, I think this is actually not what that is. I believe what the critical path is showing is just, it's marking the cycle, it's marking the instructions that have to go to the high pressure port. So basically, CP, as far as I can tell, is basically, at least on the readouts for Nehalem, is basically just telling you when there are, when an instruction issues to the port that is the high pressure port, the highest pressure port. Because there's other things I was thinking that CP could be. It could be the longest serial dependency chain, and it doesn't look like that's what it is, right? It looks like it's just literally telling you this, but I could be wrong about that. Now, the reason that I say that it still might be that is because since all of those things combined, since all of the things have to combine to the right at the end, it's possible that critical path really does still do the analysis of the longest serial dependency chain. And it's just that since all of these things are in some sense dependent, that's what it's showing us, but I don't know. So anyway, so CP looks to me like, I'll have to play with this tool more to really say, but it doesn't look like CP, at least for what we're doing, is all that interesting. But this right here is very interesting, the port thing. So, okay. With that in mind, we can go back to the routine and just take a quick look at some things that we want to sort of verify. And I was talking to Fabian. Actually, I was talking to Fabian last night. I went over to see him and Sean on the east side, and because I was already in Bellevue for the conference, and so we try to hang out periodically and just catch up. And so he actually mentioned something that I don't remember us finding to be the case. So it's a little weird, but like he was saying that you can't run programs that have the markers in them, but we were able to do that. Like this is running with the markers in it. He was saying it crashes when you get there, but it doesn't crash for us. And so I don't know if that's just luck, that GS write doesn't actually cause a problem because of some other aspect of our system or something. You know, I don't know why he said that and why we're not seeing that. But I guess we're just lucky because, I mean, he wouldn't just imagine that, right? Like, presumably he didn't imagine that it might crash. I mean, he uses the tool himself, so he must have seen it crash. But we are not actually getting that crash, so we must just be not happening to hit the situation that he was hitting, either through good fortune or because we're doing something slightly differently. So we're actually able to run with that on, which is kind of cool. But either way, something to mention, if you decide to use this tool as part of your development environment at home, be on the lookout for that, because Fabian said that it crashed for him if you ran it, so you could only use it for analysis, and then you have to turn it off if you want to run the program. We haven't seen that happen on the stream, but I don't want people to get caught off guard if that turns out to be the case. So what I want to point out here is that we have sort of, we're caught between a little bit of a rock and a hard place if we want to get our cycle count down. Now, at this point, it's unclear that we really need to get the cycle count down yet, because at this point it kind of looks like, and you know, we haven't really done a whole lot of looking at this yet, but it looks more like we are hitting memory problems in terms of the memory throughput that we can get through in order to look up the texels and to write the pixels out. It looks like that is more of a thing than our block throughput. And the reason that I say that is because if you take a look at what this block throughput is actually telling us even right now, it's saying 97 cycles. And if we take a look at that 97 cycles, if I take a look at the 97 cycles and I divide that by the fact that we're doing 4 pixels, right, you can see that we get 24 cycles out of that, right, or 25 cycles. And so if we're thinking that we should be getting 25 cycles, but we're actually seeing 40 cycles, then probably there are some stalls in here due to memory. But I want to take care of one thing first that Fabian mentioned. He was saying that one of the things that the analyzer doesn't do is take loops into account. And we do have one loop in here, right? We've got this for I loop. And so when the analyzer is going through and looking at your code, it's not going to expand those loops. So it's going to miscount the number of operations that you actually had to do. So what I'm going to do, even though it's not necessarily having anything to do with optimization, is I'm going to manually unroll this loop, since it's a very small loop, so that there are no branches at all in the code that comes out of the compiler. And that way, what we'll be able to do is get a more accurate count out of that tool. So here we go. There we got 4 pixels, right? And now all I have to do is change the I in each of these to be whichever pixel it was supposed to have been on, because that is the only thing that was actually varying in the loop was the I, right? So there's the I. Here we go with the other I. Go. And done. Okay, so let's go ahead and run this. There we go. So that is now expanded. What's interesting about that is it's also slower, which is a little bit odd, right? You can see the cycles have gone up somewhat, which is a little bit unnerving. But all right, that's kind of weird, right? I guess it doesn't like these to be expanded out. I don't know, I'll have to think about why that is exactly. I suppose one thing I should do as well is this is not a particularly good way to do this potentially for the compiler. I feel like we should probably try to reorganize this a little bit. In fact, I might just go ahead and do that right now, right? What I would kind of like to do is I need to figure out some way to get these fetches stuff out, but I guess we can't really do much about that at the moment. So I'm going to go ahead and make these into individual fetches here, like so. There we go. We get these fetches. I'm going to delete the asserts for now, since we do not have any problems with the asserts at the moment. There we go. I'm going to go ahead and aggregate our Texel guys here. Oops. You can see all that. So we've basically got 4 Texel pointers. And that will be fetch 0. And fetch, oops. 1, 2, 3. 3, 2, 1. Okay. So those are all the fetches. And then these guys are all off of each individual Texel pointer. So 0, 0, 0, 1, 1, 1, 2, 2, 2, 3, 3, 3, right? What just happened? Oh, that was dumb. Forgot to get rid of the open bracket there. Okay. So let's go ahead and run that. Make sure that's running. It's crazy how the cycle counts change, right? Like, yeah, it's kind of bizarre. That's that whole thing with stabilizer. I don't know if you guys ever seen stabilizer. There's a thing which basically tries to randomize your code layout to see what's actually affecting performance, because there's so much variability nowadays in it that the same exact code just offset where it is aligned in memory sometimes can change the performance and lead you to think that things are costing more when they're actually the same, and so on and so forth. But all right, so anyway, what I want to do here now is just group by sample, group by what we're setting for the moment. I'll have to think about if maybe there's a better way to do this, but I just want to kind of get this organized a little bit more so I can start to think about it a little bit more carefully, because we've basically got we're trying to build some SIMD stuff here, right? We're trying to build SIMD registers that have the appropriate values in them for us to do our computations. And so what I want to do is just change this so that I can actually do, okay, sample A is just an set PS, so the compiler can see very clearly what I'm actually trying to do. It's like, oh, okay, I just am trying to set one of these guys to be essentially each thing of the Texel pointer, right? Now I think this is the, there we go. This is the thing where it's always going to be the wrong one, but one of the things that Fabian suggested on Twitter a long time ago, because I was complaining about it, is he was saying, just always use set R. He was like, I don't know why they even have the other one, right? But basically, I was complaining that set PS always went the wrong way. And so, yeah, he was saying, just use this one, because that way it goes the correct way. And you can see what I wanted was I want the low value to go here, and then the next one, I want memory order, basically. And this one is in memory order, whereas set is in register order, like register readout order. And I find that super confusing. So anyway, I'm gonna use set R so I can do it in that order, and I probably will convert to using that permanently, because it's just the way I tend to think about it. And so it would help me it would probably keep me from making some careless errors, right? Where I forget that it's the wrong way or something, you know? Oops. Why can't I? Oh, right. Kill rectangle, yank rectangle. There we go. So that's correct. Oh, whoops. I guess I didn't quite mean to yank the rectangle in that way, but all right. We'll live with that. That's fine. So there we go. And let's get this one. Wow, I am sloppy typist tonight. I was really exhausted I hadn't been sleeping all that well. Sometimes my sleep schedule gets really off, you know? And I just I have a hard time falling asleep. That's just how it is. I don't know why. I've always had a really hard time falling asleep. Like, I can't just go to sleep for whatever reason. And sometimes it's just like, I don't know. It's really annoying because I wish I could like always keep on a regular schedule because it makes a lot of things easier for you, obviously, because you know the world operates at a particular time. But what the long and short of it is I have not been sleeping too well because I've been getting up relatively early, but I can't seem to fall asleep, so I don't get that much sleep. So I took a nap today, just before the stream actually, and still a little groggy. But anyway, so I'm going to go ahead and get this all working properly. So no, I switched under warning. All right, conversion uint32 to float. Oh right, these are supposed to be set EPI 32s, right? Hopefully there is one of those. Yes. Forgot we're not setting packed singles. We're doing packed integers. Okay. There we go. So let's go ahead and run that. Okay. And God, it's so weird, you know? It's just so weird. The cycle counts. Now we're magically faster than when we started at 40 cycles. Yeah, so much variability. Like you'd think that's basically what the compiler would have already done. It's not. So that's okay. That's maybe it was hard for it to figure out that these were fusing like that. So yeah. But anyway, so there we go. I don't know. These all look relatively sane to me. Like I don't think we're doing anything particularly stupid here. That's how we have to access that texture memory. So that seems pretty reasonable. There is one thing we could do here. I don't know if we want to do it, but we'll try it, and we'll see if it makes a little more sense. And like I said, I'm probably planning to go pretty long today. I'm in the mood to do some programming. I haven't programmed in like 2 days, which I get grumpy about. I mean, I did do a little bit, but it was for a separate thing. So anyway, taking a look at these here. In fact, one thing I guess we'll want to do now, I might want to check out here. We've got O2 on, right? Yeah. I want to take a look at that total throughput count now as well, right? I just want to get that readout. And so 103 cycles. So now, at least in theory, this 103 cycles is actually the number of cycles that the thing takes, because the loop is actually unrolled, so it's accounting for all of the instructions that actually have to occur, right? Before, it would have had a test and a jump in here, and that test and the jump, it would not have actually counted how many times through the loop it would have had to have gone. And you can understand why, because most of the time the loop's not going to be over a constant number probably. It would be over a variable, and it doesn't know what the variable's value will be, because it's looking at the code. It doesn't have the state of the thing at the time. So there's that. Okay. I need some more soy milk. Hold on a second. I ran out, and that's no good. Okay. Oh wait, did I say soy milk? I meant almond milk. Sorry. I need more almond milk. I do drink soy milk occasionally too, like in coffee. Like if you go to a coffee shop, I'll get soy milk sometimes. Sometimes they have almond milk, which is good too, but a lot of coffee shops originally only had soy milk for people like me who can't drink regular milk. All right. So anyway, what I wanted to see here, I was just thinking like, oh, maybe we could go through and we could, since we know, like you can see like these two guys here, when they're actually doing these fetches, I feel like, well, No, you know what? I think that pretty much has to stay the way it is, now that I think about it. Because it could be fetching any other texel because of the way that it's stepping through there. So I don't know that there's really anything else we can do here. When we actually load these things in, here's what I'm thinking. So you see how these guys here, we have texel pointer 0, 1, 2, 3, and then we immediately load texel pointer 0, 1, 2, 3 plus one integer over. I was wondering if we just did a load U on that. I was wondering if we could just load it and then do a load once, and then from just doing the load once, grab out the two values that we needed. That's what I was thinking. And I'm not sure that that actually saves any time. Like, I'm not sure that actually does anything for us. But that is what I was thinking. So, like, you know, if we went over to the Blackboard, just to give you a little bit of a feel for what's going on there, right? If it's day 121, what I was thinking was, okay, so we know that when we load the thing, right? We know that when we load it, what we are doing is we're loading this texel, and then this texel, and then this texel, and this texel. So this is 32 bits. This is 32 bits. So I was thinking we could just load this in one load, right? Just load it once. And when we load it once, we then would have a register that would have, like, you know, the 0th one here, the 1 here, and then two things we didn't care about here, right? We could also try to do a 64-bit load, which I think we can also do, where we just load these two. I can't remember if that works well or not. But we could do those and then just grab it out of the register. I don't actually know why that would be any faster. I suspect that it probably wouldn't be, but it might save some kind of work where you know, things didn't have to happen quite the same way. So we could take a look at that. The other thing, you know what we should probably take a look at, and we should probably have up while we're doing this? Nehalem architecture Wikimedia diagram. So this was kind of a handy diagram someone pointed to the other day on the stream. And the thing that I kind of liked about this was it actually let us see some stuff about what was going on. Like, here's the floating point adder on port 1. Here's the floating point multiply on port 0, right? It also has, like, some other information, like it has an integer ALU on each of these guys, which I assume that integer ALU means we could do integer adds on multiple ports or something like this. Not actually sure. So it would be cool if we could find something that actually had a really explicit listing, because one of the things that's kind of annoying is once we actually put an instruction in here, we can see which port it goes to. But before we put an instruction in here, we have no idea which port it goes to, right? Because the Intel Intrinsics guide, like we were using before, right, like this thing, the Intel Intrinsics guide doesn't actually tell us anything about that. You know, we go in and look up one of these routines, right? Like, I want to know how something works or whatever. When I come in here, I don't actually know what that's going to do, right? I don't know what port that's going to go to. So if I want to do like one of these guys or something, you know, it doesn't tell me any information about what port that goes to. It'll tell me the throughput information, which is like kind of has a little bit of that knowledge of like what it's going to do built into it, but it doesn't tell me anything about how it would issue in tandem with another instruction. So like the add and the multiply might both list a throughput number, but it doesn't tell me whether the add and the multiply could go together and therefore overlap, or whether they would have to be serial because they use the same port, right? And so it would be nice to find, and I suspect that this is something that I can sort of go off to the stream, push off to the stream here. But basically, like, if there was, it would be pretty cool if there was a resource similar to this one that would allow you to quickly, without having to page through a bunch of stuff, quickly get to the port assignment information so that you could see when you were using instructions which ports they were going to go to without having to actually first do them and then look and go like, oh, okay, max is on port 1. It would have been cool if it had just been in here where I come down and go. Maybe I'll send it to Intel and be like, please. Because you could imagine adding to this tool a thing which basically like, I mean, in fact, they already kind of have, since they already have it per architecture, they could just have port, maybe. And, I feel like that would be just a good extra piece of information to have, is all. Anyway, maybe I'll send them that. Who knows? Maybe they'll listen. Intel is they have developer relations. They might be like, oh yeah, it's a good idea. Let's do it. You never know. Anyway, so the thing I was thinking is like, yeah, when we're doing these loads, I do wonder if the compiler is actually doing the best job of managing those, and if there's something we could do to help it understand what it is that we're doing better so that it can produce better code. And I don't actually know if that's true. In fact, I don't really know what it's doing at the moment. So it is possibly the case that we should, try to take a look at where it's doing those loads and figure out what's going on. So I suspect that is what's going on here. And you can see that it's doing like a bunch of these mobs here. And it looks like, just looking through it here, move DQA, XMM words. So those guys, yeah, are the 4. So I feel like that is this is what looks like to me. It looks like this is us loading in, us loading in all of our Texel data there. And let's take a look if that holds any water. Let's see here. It's doing the unpack. It's doing punpack load q ldq psr ld, and then it's doing the pan. So yeah, I think that is what this is. So if it's doing that, what it's doing is it's doing a bunch of move Ds. How many is it doing? It's doing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Looks like that's all of them, right? Although, well, we've still got some of these guys up here. I don't know. Because we're not doing any loads up here. We're just doing the loads in here. And then everything else doesn't actually have to do any loads till we get down to actually doing the load for the destination, right? The destination is the only other load that we do at all, right? These guys here. So I don't know. It looks like if it's shifting by 8 there, it looks like it's doing this operation. And it looks like it's doing that directly after. This is hard for me to read. This is largely probably due to the fact that I don't spend a lot of time reading this kind of code. So it's harder for me to kind of like parse through it quickly. But I'm not sure, so I don't know punpack ldq. Can we take a look at punpack ldq? Because I'm not familiar with all the instruction ones by name, but that's not something we called explicitly, if I'm not mistaken, right? That is actually an unpack intrinsic, which if I remember correctly, we don't use, right? So the compiler has decided to do the unpack itself. It felt like that was the right way to implement this. So that suggests to me that it actually, so it kind of redid how that code, how it thought our code should work, right? it's unpacking the load. So if we're loading one of these guys in, it's unpacking that load. Where did we go? There we go. It's unpacking that load. And then it just goes ahead and unpacks it twice. Right? So you can see here it's loading off the pointer into XMM1. It's loading another one in on top of it, but first it unpacks that, then it unpacks it again, and it's got XMM14 now, is the result of a double unpack, right? So the double unpack, the next time it takes a look at 14 is here, when it actually does the shift. So just trying to reverse engineer what it's doing there, right? It looks like that once it loads something, it is actually going ahead and jumping straight to here, right? So sample A8. So the way that it chooses to produce sample A, which we have told it to do this way, is to do a load and 2 unpacks. Am I missing something? Here's the load into XMM1. It unpacks XMM1 to XMM2, unpacks XMM2 to XMM14. XMM14 is never touched again. Oh, no, there it is. It copies it over to 0, right? And you can see why that is, because it has to use it twice, I guess. So that makes some sense. It copies it over to 0. It shifts one of them down. It does the add with 0 and 1. It does the and with 0 and 1. It does the and with 14 and 1. So that's doing this right here, right? Because I'm assuming that XMM0 in there is what contains the mask. XMM1 is what contains the mask FFOOFF, right? Because it's doing that and with both of those. So I'm assuming that somewhere in here it loaded up XMM1 with that value. And I'm assuming that that's probably, where is that going to be? It's going to be the last time we touched XMM1. It's that. And so this right here is called RIP relative addressing. Also, I believe, again, I'm not the assembly language guy. Ask Fabian. Or find another assembly language expert if you want to. I feel bad we're forcing Fabian to do all our homework for us. But as long as he's willing, he's a good person to ask, so we'll take advantage of it. So anyway, basically what this is it's a cheap way to do extra addressing. Essentially, the instruction pointer, like where you are in the code, you can actually do loads off of that. And it makes it easier to load in constants, basically, is what that boils down to. And so this, I assume, right here is what's loading in the FFOOFF, and then it's going to AND with that. So it basically just did unpack LDQs, and it did 2 of those. It looks like it's doing 2 of those per sample. I'm sorry, per load, per fetch instruction, right? And to be honest, I don't really understand how that's working. I guess it's doing it as a shuffle. So the unpack, presumably it's loaded XMM2 already. Where is XMM2? XMM2... right there. Okay, so XMM2 got loaded off of R9, which I'm just going to go ahead and assume is another one of our texture pointers. One of the like an address into the texture. So it's taking XMM2 and it's p-unpacking it out of XMM1. Sorry, I should be more specific. P-unpack, we covered the unpacks before where they kind of interleave values. So it's interleaving that XMM1 load with the XMM2 load, and then it's going to presumably XMM14 was loaded somewhere up here as well. There it is. So I guess What that suggests to me is that the compiler is kind of already doing a very smart thing for this. Like, it's actually doing it as an interleave, which would make it way more efficient than what we wrote here. So I'm going to go ahead and say that actually this is okay. It looks like the compiler is actually doing a pretty smart job turning those into unpacks, which is what we would have had to do to make them more efficient anyway. Yeah. So that was good. That was worth looking into, because now we know we really don't have to play with that. I don't think I could think of a better way to do it than 2 unpacks. That sounds pretty good. Yeah. So I think this is fine then. I think that's okay. I think we can be reasonably happy with that. This stuff, on the other hand, I don't really know much about, unfortunately. This is something that I've never really worked with before on SSE. And so specifically this stuff right here, the fetching, in order to do the fetch, we have this problem where, oh, well, so there's a couple stupid things. The compiler may have already figured this out, but I'll interrupt what I was about to say to point out the fact that we multiply by texture pitch 4 wide manually, which is stupid, and we multiply by size of uint32 manually 4 wide, which is stupid. So hopefully everyone on the stream at this point could figure out, without me having to say it, that really how we should have done this was, before we did that, we should have done the multiply wide. If we're going to multiply each of these values by texture pitch, we should just, each of these values by texture pitch, we should just multiply fetch y4x by texture pitch and then extract it afterwards, right? Now, I don't know whether the compiler already did that or not. So it might be that it was kind of cleaning up our stupidity. But I feel like we should probably just go ahead and put in that just in case. And let's take a look here one more time. Oops, let me recompile this. There we go. Let's take a look at that one more time. Go up in here. So right now we're at 103 cycles. I'm just going to go ahead and do that multiply here. So this is an mul EPI 32, right? And I want to multiply fetch x for x. I want to multiply that by texture pitch. Oops, sorry. Size of uint32, right? And you know what? I guess size of uint32, though, I don't need to multiply, because I know that size of uint32 is just a shift. So I could do it by an immediate, so we don't have to use another register for that. If that makes sense. Meaning, I know that to get something to go up by the size of a 32-bit integer, I really only have to shift it up by because this is the power of 2, right? This is 4, so it's 2 to the second power. So I should be able to just shift it up by 2, if that makes sense. And that would give me the value. So if I want to, I could do the shift left by immediate and just shift it up. And that's, that would get rid, I guess is what I'm saying, of this. Right? So like that. I don't know why I deleted that. I got to keep it in here for now. We still have to extract these. But so yeah, so if I was to do that, right, that should give me what I needed in terms of stepping, right? So there we go. And then similarly, this guy right here should have just done, fetch y4x equals mul ps, and that should be the texture pitch that we've got there, right? So texture pitch for x, and fetch y for x, and now those are gone. And so yeah, so the compiler may well have, oh, God, it's just like, it's like Casey's stupid weekend here, isn't it? I mean, well, it's our unstupiding weekend, but, right? I mean, what's going on here? That's a 4 wide add, people. Like, why am I making the compiler have to do that when it shouldn't have to? Should at least give it the wide stuff so that it can see it as wide. I feel like that would generally be better anyway. So yeah. Oh, and this is, why did I do PS? add EPI 32. All right. 4x, 4y. Yeah. You know, it sometimes takes you a little while to see each individual thing that you should be collapsing. You know, I don't claim to be an optimization guy, and it's true. So let's go ahead and set1 EPI 32 that so that we have that guy there. We can probably clean up some of these. Some of these are probably just not even used anymore because we shuffle stuff around. But anyway, texture pitch 4x, that's just texture pitch, right? Oops. Texture pitch, like so. And I feel like, I don't want to jump the gun here, but I feel like, what did I do wrong? Cannot convert, yes, that's true. Sorry about that. I feel like there's plenty of other stuff we could do here. Oh, it looks like we still need that. I don't know if we want to re-extract is the only thing, because otherwise we could get rid of that as well. But anyway, texture pitch, texture pitch. All right. So anyway, there's another thing we could still do there, I suppose. Oh, that doesn't look pretty. That doesn't look pretty at all. What'd I mess up there? So shift left by 2 of fetch x 4x, and then mul EPI 32 of fetch y 4x by texture pitch 4x. Excuse me. What am I missing here? Oh, I'm not missing anything. I just forgot to get rid of the, oh wait, oh, that's correct. Yeah, so what am I missing here? This should multiply 4x by 4, although, I mean, well, you know what? Why bother guessing? Might as well just step through, check it out. We'll see what goes on. All right, so if we go in here, and yeah. If we go in here, let's find out what happens. So we have our fetch x 4x, and I want to see that as I32s. M128I, oops, M128I, I32. 11, 12, 13, and 14 are the values that it looks like we're getting there. I guess that's kind of commonly going to be the case for rectilinear blitz. They'll often go in series if they're not rotated, right? Does that make sense? Multiply by 2. I'm sorry, by 4. That does look like it multiplied by 4, right? I feel like. So fetch y. Nice. Fetch y 4x. Fetch y 4x. And 128I, I32. These are all from the 0th row of the texture, also not surprising. So we won't find out much about this. And so then when we get to the fetch 4x, M128I, I32, let's see what we get here. So that looks like what we would want, right? Those are the pixels. So that looks correct to me. Right? It don't quite see what the problem is there. All right, well, let's step through and do a y that's not 0. See if maybe something obvious is going wrong, because it's hard to say. Hard to say about that, I suppose. Yeah, that's about right. Let me get to some kind of a y that's not at 0. There we go. So we come through here and we do our fetch y for x. Here we go. And I want to take a look at what texture pitch for x is. And that's M128I I32. Oops, I32. There's our texture pitch, 324. So now we're going to do the multiplication of fetch y for x and texture pitch for x. You know what I just realized? That might be my problem. Shouldn't this have a mul low and mul high in it? I'll check that out in just one second. Let me go ahead and step through this here. So fetch y for x is this guy right here. It's got 1s in it, so it should come out to all those. And it doesn't. That's the problem. Duh. All right, so what that was just me being hasty and not thinking it through. Mul EPI32 does not do integer times integer. It does 32-bit by 32-bit out to a 64. So it probably only does the low integers or something like that. That's just that's not the instruction I was even thinking of, right? So you can see that here, mul EPI32. Oops. It's not even in SSE2. Mul EPI32. See, it just grabs those two lows and then produces the full 64-bit result, which is not in any way what we want. What I actually wanted to do is just multiply the two values together. I don't know what that just did. Do not want to know what hotkey that was. I actually want to do a thing here where I'm just taking the low. I want to take each of the 32-bit lanes, multiply them together, and just take whatever the low is of that result, right? Because I'm pre-saying that it's not going to overflow into. I'm saying that they're going to be small enough values that they won't overflow into a 64-bit result, right? And so in theory, that should fix it. Yeah, and it does. Okay. So that was a good thing to remember. Don't forget, there is a mul command. You will be able to do mul EPI32 by accident and then forget that that is not at all what you probably were trying to do. So there you go. All right. So I'm imagining maybe the compiler was smart enough to do that for us anyway, but there we go. Now, one of the interesting things here is we could actually do the texture memory add as well, meaning we could just do that add for wide, but on 64-bit processors, that's actually a 64-bit pointer potentially, so I don't want to push it, I don't want to push it that far, if that makes sense. So, yeah, so that's about it. I don't know that there's anything else to be done with just that unpack situation here. But now the most important part, it was good to just kind of clean that up a little bit just so we're not forcing the compiler to figure that out. What I do want to do, though, now is get back to what we were sort of looking at originally, which is that port pressure, right? So here we go. So who is our port? Who is our we're on O2 here, yeah. Who is our pressured port? Our pressured port. We're back to interiteration, are we? So someone was saying that interiteration is what happens when it believes that if you were to run the block repeatedly, that would be the problem. Meaning it would be dependencies between loops or something like this. That's what someone was saying. I haven't read up about that yet, so I'm not sure if that's actually a meaningful thing. But it actually looks kind of like, to me, yeah. It looks kind of like, to me, that we kind of have things a little more spread out here. It's weird because one of the things that's, I guess, kind of difficult to work through as well, you know, when I'm looking at this, and again, this is the first time I've ever done SSE, anything with this tool, is that the cycle count doesn't necessarily match up with the cycles per pixel that we observe, and presumably that has a lot to do with how the memory actually works out. Like, in theory, I feel like that this one should have been slower because it says 116 cycles, but I feel like we had 101 cycles up here, and that one was actually not faster, though, when we had it going this way. So I don't know. A little bit odd. Anyway, point being, we do have one thing that's kind of bizarre, right? And we looked at that the other day, and it was because I wasn't actually sure how to use the tool. It was a bit of a problem. But one thing that we did is we tried taking the bilinear and making the bilinear unpack be done in 16-bit per element instead of doing it as 32-bit per element, right? So we were basically, instead of doing multiplies with the floating point unit, we did multiplies with the 16 wide lanes. And there's a number of things that we could do there. Like, we could try to continue that on and do 16-bit further through the pipe, right? We could try reverting this back to doing the floating point, because since we know that we have too much pressure on port 1 in a lot of circumstances, moving the pressure over to port 0, which is what we had before we did this conversion, might be helpful, and so on. But the problem, as I see it at the moment, like I was saying, is that I feel like we have a memory problem as well. Which is to say that if we take, for example, what this tool thinks is the number of cycles that we might have, we are actually observing more cycles than it is reporting, which would suggest that we're not getting stuff back as immediately as we should, right? It suggests that there are some longer memory latency stalls in there. And so one thing that we might want to do at this point, and one thing that I'm considering, is now might be a time to try to switch to multi-threading in the renderer. And the reason for that I say that is because if you take a look at how these sorts of things work, remember I talked about hyper-threading before? So the way these Intel processors work on anything that has the hyper-threading in it is that the idea behind the hyper-threading is actually pretty simple. If you imagine the processor has these units, right? Excuse me, I have to blow my nose. So when we talked about the diagrams, and I mentioned hyper-threading at the time, but I'm just going to mention it again. So we know the processor has these units, right? And the way that it looks at any given time, is the processor maybe is in there, and let's say, it's got an FP add, right, unit or something that's adding floating point numbers, and then it's got, some unit over here that's like doing loads or whatever, right? And so, the thing issues a load, and it issues a floating point add or something, and those are going through the timeline. We've got our ticks here, right? Tick, 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 right? So here's cycle 0, let's say. And if we issue one of these FP adds and we issue a load, let's say we issue both of those. We issue like the add and the load both on this cycle, right? And let's say the load hits the cache perfectly and the add works out and whatever. So like the total amount of time, maybe it takes to do this thing is just like, maybe it's only 2 cycles or even just 1 cycle. And so the results come back like right here, and it's totally fine. Or if they were long latency, maybe they take this long, let's say, 5 cycles or 4 cycles or something like this. But once they're in there, we can also issue some more things. Like we've got more things to issue. So we issue another add and a load, and we can issue another load or an add or whatever, who knows, right? And they go into the pipeline and they complete serially. So like this guy completes over here, and this guy completes over here, and whatever, right? Again, this is nothing specific. I'm just saying we've got things going into these units, and then we've got things coming out of them, right? And from the perspective of like this tool, what we're looking at is saying, let's make sure we can always issue. Let's try and figure out how to minimize the number of things that go, the minimum number of instructions to any one port. We want to try and minimize the maximum number there, right? Because the maximum number is going to be how slowly we run. Because you can only issue to that port serially. So even though you can issue as many things as you want across multiple ports, you can issue up to 4 or whatever it is. You can issue a certain number of instructions at any given cycle. You could only issue 1 to any given port on that cycle, so that becomes the bottleneck, right? But if we are having a problem where the inputs to these, right? Because like an add or a load has inputs. It's got like the address or the things to add. If we get into a situation where the inputs, the sources, are not here yet because they're coming from memory, we're waiting for them to arrive. What we can end up with is a situation where all of the instructions, like we get to some point, and all of the instructions that we could issue, all of them, all depend on some loads that have not arrived yet. Because like the load takes, 100 milliseconds or, 100 cycles or something. Wow, 100 millisecond load, that'd be awful. And so there's this big, huge window, and there's nothing we can do about it, right? So what that means is at that time, when we get to that stall, right? When we get to that point where we are completely waiting on inputs from memory or a slower part of the cache, an L3 cache or something, or an L2 cache, probably not an L1 cache, because those are very fast. But when we get to the point where we're waiting on that, we've got all these units that are sitting around doing nothing. Like we could stuff another load into the load pipeline. We could stuff another FP add into the FP add pipeline if only we had one to put in there. So the units are basically just sitting there doing absolutely nothing, and that's a huge amount of wasted performance for us. So what hyperthreading attempts to do is take advantage of the fact, these are called latency bubbles, right? And they're basically like little bubbles of time that form because we're just waiting to have something to put into our units, right? What we can do with hyperthreading is say, well, what if we just had 2 streams of code, right? So here is loop 0, and this is loop 1. And what if we were just to run both loop 0 and loop 1 at the same time on the same processor on the same core? So it's still entirely single-threaded in some sense, meaning there's only one thing executing at a given time. But what can happen is it'll execute loop 0 till it hits one of those bubbles. And it hits a point where it goes, I'm completely starved for memory. I can't get what I actually need to get in order to issue any more instructions, and the units on the processor will just go fallow. What it then does is it immediately task switches over to loop 1 in a very, very fast way. It's got like a special bank switching ability to make it so that it doesn't have to do like register, save, and load from memory. They're like all the processors like ready to go with them. That's what makes them a hyper thread, because it's a thread switch that doesn't go through the operating system in that way. It doesn't have to like ask the operating system to manually do it, right? Which takes a bunch of time. So in that memory bubble, it can go ahead and switch over to loop 1 and see, does the other loop have any instructions that I could fill in here, right? So it's basically this way of giving the processor more potential things to do, so that when it gets to some point in the loop, when it's waiting on memory and it's like, it can go over to the other loop, which will have some instructions to execute. It does those, and when that guy hits the part where he's waiting on memory, it ping-pongs back over, right? It comes back to the previous loop, and we hope that now all the memory we were waiting for on that loop has had time to arrive. And so that's what hyperthreading is. So what I was thinking we might do, because we want our renderer to be hyperthreaded, what I was thinking we might do is hyperthread the renderer. so that we can start to see real performance measurements of something with hyperthreading on, so that we don't do a bunch of work to optimize memory latency that we don't actually need to optimize, right? Because a hyperthread would have just done it. Again, with anything with optimization, it's very hard to know whether you're making a good decision at the time, unless you've had a lot of experience. And I haven't. Like I said, on x64s, I do pretty light optimization. So it's a little bit hard to tell, but that was just something that I thought of. I was like, maybe we should switch to that earlier rather than later. So that's actually surprisingly easy to do. It's not that hard. So I don't know if we want to do it and make this like a marathon stream or whatever, but we could do it now. Maybe what we'll do is we won't actually try to multi-thread the renderer too much, but I'll show how to actually get more than one thread working in Windows, for example. We could at least do some of that before going to the Q&A. So let's take a look in here. Threading. You know what we could do? I wonder if we should just break this up into 2 days, though. Because if I introduce threading... You know what? I'll do it the other way around. That's what I'll do. We'll introduce threading on Monday, but what we can do is prepare the renderer to be threaded. That's what we should do. Yeah, that's a better idea. And then we'll have one day that introduces threading. Okay. So what we need to do to get the renderer ready for threading, really, we can do something pretty simple. There's 2 ways we could do it, and I'll sort of say a little bit about how I'm thinking about it, and I don't know. It's hard to say what the right decision is. We can try a couple different things. But here's what I think would probably be smart. So we've got a screen, and we know we have to render this whole screen's worth of stuff, right? And what we also know is that typically what we are drawing is rectangular, right? It tends to look like that. You know, it doesn't look like this. You know, we're not drawing very many things that are long, slivery. It doesn't look like this, you know. It doesn't look like that. It tends to look like this, and when it doesn't look like this, it looks, you know, like a rotated version of this or a smaller version of this, but it's very much this way. And so remembering that we want to try and optimize to make sure that we don't have things being in and out of the cache a lot and that sort of thing, we want to try and design how we're going to break up the rendering for multi-threading in ways that don't put lots of extra pressure on the caches. So what does that mean? Well, we've got 2 things that have to go in the caches, right? We've got 2 fundamental pieces of memory that we are working with, right? Technically 3, but one of them is probably not very relevant. Okay, so I'll say what they all are. We've got 0, 1, and 2, and I'm sort of saying that 0 is probably not super important. 0 is the command buffer, right? That's the thing that we've got there, that render group that basically just says all of the stuff that actually has to happen when we render, right? And I don't think that's going to cause us a huge amount of headache because it's just not accessed that frequently, right? The number of commands of the command buffer versus the number of pixels and texels that we touch is just not that relevant. So even though this technically is a piece of memory that we have to access, it's not really relevant, I don't think. So okay, we've got that. We've got a much more important thing, which is the frame buffer, right? The actual thing that we're writing to. Ooh, what did I do? Oh no. No, what happened? I don't know what happened. I hit Control X. I don't know what that does. Control X. Doesn't even look like that's a thing. Control X. This is a great, wow, there's a hotkeys window for you. All right. So anyway, maybe I just hit Control S accidentally and it just saved. I don't know. Anyway, well, hope it was nothing bad. So there's the frame buffer, which is obviously, you know, a huge thing that we're writing to and reading from. So this is basically a read-write thing. And then we've got our textures, which are read-only. right? We never write back to the textures. Now, once in a while, the frame buffer might actually be something that we texture from. So we do have, in a sense, some read-write textures, but we're just going to really treat those as frame buffers, right? That's when we're producing like our ground chunks. We write to the ground chunks first, but then we draw from the ground chunks later, potentially, right? So it's a little bit weird in that sense. But anyway, so that's how that works. And if we think about this, what that means is that in terms of our managing how the memory flows to the system, what we're trying to do is minimize the degree to which we load from these and read and write from these things in ways that are spatially incoherent, right? So like what we don't want to do with the frame buffer, for example, is we don't want to have a situation where we like read and write some part of the frame buffer, read and write some other part of the frame buffer at a size sufficient to blow out the cache, meaning like we completely replace like a bunch of stuff in the cache with new stuff, and then go back and read and write the exact same stuff again. Because basically what that would mean is we've filled the cache with something once, we've then spent another whole amount of time to fill the cache with completely other things, and then we've gone right back and filled it again with stuff that was already in there before that we could have had for free if we'd just done the work at that time, right? So what we're trying to do is do a little bit of management of that locality here so that we can avoid that process. Okay. So the first hack I'm going to take, just to try, is I'm going to try and manage the frame buffer locality. And the reason that I'm going to try to manage the frame buffer locality is because managing the texture locality I feel like is going to be harder. The reason I feel like it's going to be harder is because there's rules about what has to be drawn texture-wise in what order. So it's not like I can necessarily sort things by the order in which they use textures, because we have to do things like sort them by the order that they stack up on the screen and other things like this potentially for other reasons, like getting the correct result and other stuff like this. But the frame buffer, it's pretty free for me to pick how I want to dice up the frame buffer, right? I can, for example, if I have two threads, choose to just break the frame buffer in half and have one thread render one side and one thread render the other side. And there's no there's no constraints on how I do that. I can literally break up the frame buffer any way I want, and it doesn't really affect anything else in the system. So I'm going to try it that way first. And so what I'd like to do is I'd like to design it so that we work potentially in chunks of the frame buffer, right, that are sized appropriately for the cache, right? Meaning I would like to break up the frame buffer into pieces which I think will fit into the cache in a nice, in a way that if I was to just operate on everything inside that region, I wouldn't blow out the cache too much, right? It could fit into the cache nicely. So there, it's not a region that's significantly larger than the cache is, right? Now, unfortunately, I don't actually know what the cache size is on this particular processor, but I remember it was like a W5580, right? And so, on this particular cache, on this particular processor, we could see what the cache was, because usually they'll list that sort of thing. Let's see here. Do they have L1, L2 listed? Might have to look at a different place for caches. L1 cache size, for example. How big is it? There it is. Halem microarchitecture. So let's assume that that's somewhat right. Although I feel like, how can this is a little little weird. I feel like, because I don't feel like the cache size is constant for across all Nehalems, right? Is that actually true? Maybe it is. So it might be that all Nehalems have the exact same L1 and L2 cache, and it's only the L3 cache that changes, right? But anyway, if you take a look at this, you can see like the L1 cache is 64K, the L2 cache is 256K, right? So if we thought about how big that was, right? If we thought about how big that was, how big of a square that was even, just to get like a ballpark value, right? You can imagine, I've got square root of 256 times 1024 is 256K, and I know that each pixel is 4 bytes per pixel, right? So if I want to know if that's how much pixel area there is or whatever, right, that's how big that thing should be. And you can see it's actually a 256 by 256 square, right? So 256 by 256 by 4 bytes per pixel, that ends up being 256K. So roughly, if we were to take up the entire cache with the frame buffer, which obviously you can't actually do because you need space for the other stuff, like loading for the textures and these sorts of things. But basically, the size of the L2 cache is actually a 256 by 256 square of 4 byte pixels, right? So thinking about that for a second, that means that, you know, if we were to take our current screen, like how many tiles across we would have, what were we at? We're at like a 1920 divided by 2, right? We're at 960, right? So 960 divided by 256, right? 3.75, so almost like 4 across, and 1080 divided by 2, 540. That's like 2 and a little bit across, right? So like I said, we can't really do that size because it's just it'd be a little too big for the cache anyway, but I don't really know exactly how big we would want it to be, so we'll probably have to play with that size a little. Like the only way to really know, I think, would probably be to like adjust the size a little. But we can start to see sort of what the size would actually be, right? Like let's say we did maybe you know, something like 128 by 128 by 4, right? So it was a 64K size. And, you know, that would be one way we could try to say, well, that should fit in the cache pretty well, whatever, right? So, you know, that's an example of how we could do that. Now, we probably wouldn't do it exactly on a power of 2 size because we need to divide evenly. So our 1920 divided by 2, 960. So let's say we took that 960, right? You know, and you could imagine dividing that into 6 chunks, let's say. So they'd be like 160 is relatively close. So let's say, you know, 160. What's 160 divided by the sort of the width of the thing? We know we load 4 pixels at a time. So that'd be 40 pixels. So we could do, I'm sorry, not 40 pixels, 40 warps of 4 pixels. So we know we could do like, you know, sort of 40 warps across by however many warps down we wanted to do. Could be a chunk, right? So what I want to do is I want to figure out a way that we can have the renderer easily break things up into chunks. And then what I'm going to do is multi-threading wise, meaning when we actually are using multiple cores of the processor, I will assign different chunks to different processor cores, so they can each work on a different core, part separately. But then the other thing we will do is for hyperthreads, we will treat them specially, because what I want to do is I want to maximize the likelihood that textures hit the cache as well. And because each individual core, right, you can see on each core it shares a cache. So like the L1 cache is shared on the cores. The L3 cache is shared across cores, but the L1 and L2 are only shared on hyperthreads inside that individual core. So what that means is that while I do care about texture locality to some degree, you know, I've got 4 megs, 8 megs. On this particular processor, I think it said 8 megs. I've got 8 megabytes of backing in the cache for the textures. That's a lot. But for the frame buffer, I don't have very much necessarily, because if I want to keep that local to the core and I have hyperthreading, what I might want to do is take and try to dice this up in a way where the pixels getting hit by the hyperthreads are like very close to each other in terms of what they need. So that like if a texture is filling it here, it's very likely that one hyperthread will be like doing these pixels while the other hyperthread is like doing these pixels. Just try to do it, right? See if I can get it to be in that way. And so what I might want to do is not use rectangular breakup for the hyperthreads. Maybe what I do for the hyperthreads is interleave scan lines, right? So basically, like the scan lines on the hyperthreads, it's actually doing like every other scan line is a different hyperthread or something like that, right? Just something to think about. I don't know if that's a good idea. I'm just throwing it out there. But I was thinking that that might be better. It might end up being a better way to do it than breaking it up so that they don't share any of the frame buffer and each hyperthread does a different one. Because since I know they're on the same core, I just think that might be better. Just a guess. So what I was thinking of doing is basically setting up the renderer so that we have essentially a dispatch which does, render this rectangle, render this, subrect, basically, of the frame buffer, and you're either even lines or your odd lines, right? This is how it works. And then we just dispatch, we have a thing which will basically go through and do that across as many things as we want. So we can basically just set parameters at the top of it that say how many rectangles, what their layout is, and then it'll issue even and odd lines of each of those to each core based on, which ones are on which threads are on which core. So that's what I'm thinking, right? So we can simulate that pretty easily, right? I can turn this off for now. What I can do at the very first thing is I can say, well, doing even and odd lines is really pretty easy, right? All that involves is a pre-step to step, to start one down, like y min would just be pre-stepped down by one, right? So we could basically just do like, if even or whatever, if you're the even lines or the odd lines. So I guess if you're the odd lines, y min plus equals 1, that'd be about it, right? So when we do this thing where we do y min yx, we just do it that, right? That'd be all there is to it. And I assume that when we do our, I can't remember exactly where we're doing that buffer memory. Yeah, we use y min, so it would just work properly. Right? So, excuse me. So, if we take a look at this, that's all we would have to do to support odd lines is that, plus now when we actually step our pixel pitch, you can see down here where we do buffer pitch, we just have to make buffer pitch be a thing that we pre-compute differently, so that right here where we do our, our row advance might be a better word to call it. When we take that buffer pitch, we would just take the buffer pitch and we multiply it by 2, right? So really, you'd get a thing where y is incrementing by 2, and the buffer, we use twice the buffer pitch for the row advance, right? And that would now draw like basically, almost like a screen pattern, right? It's only going to draw every other line when we call this routine. So if we look at, we should be able to see it happen. And I'll just go ahead and do bool 32 odd here, right? And what we can do is we can just pass true, to do those lines. And what we should see now in theory is when I run this, we should just have every other line being drawn, right? Which it just won't draw some of those lines, right? And you can kind of see that's exactly what it's doing there, right? It's only drawing every other line. Although, it looks a little, why is it blinking out? It should always still draw. Oh, all right. Yeah, I just realized something. That's not quite what I wanted to do there. If I say only draw the odd lines, it has to first see whether it's odd to figure out whether it should pre-step it. Right? That was pretty dumb of me, actually. Draw a rectangle quickly. So if I say I want to draw the odd lines, I first have to see whether it's odd or not to know whether I step, right? So what I would actually need to do here is say like, okay, if I'm odd, and y min is actually odd, right? So I would have to say if y min mod 2, I should probably do if even and y min mod 2, because that's what that tells me. go. So if I'm supposed to draw the evens, but the y that I was going to start on is actually odd, then I have to move to the next line, and then I can go, right? And then I can do it. So yeah, okay, so there's that. So that's more what I was trying to do here, but I still don't understand the flashing. I feel like I still got one thing that doesn't make sense, because it should just look exactly like only every other line is being drawn, and I'm not sure why that isn't what it looks like, right? Like, I don't understand, like, if you look at that, I don't understand why I'm getting a yellowed version of the guy here and a non-yellowed version of the guy here. That does not make sense to me, right? Because what I should be seeing is just an every other line version of the thing, right? That's what I should be seeing, I would think. Now what I can do is make sure that I clear, I don't actually know if we clear the frame buffer. We do, we clear the frame buffer. So that should be working, and it doesn't make super good sense to me. All right, so let's try to figure out why that is. Also, I want to try draw a rectangle quickly. If I change this to false, we should see the other lines, right? Yeah, so that's just not, I've done it incorrectly. I did not do what I wanted. Oh, yeah. Well, so for even and we're on an odd line, we need to add, but we need to do the opposite as well. So we kind of need to do, this is more of an equals, right? What we need to do is this. We need to say, right, I don't know how to draw this out in the best possible way here, but so this is what we do. This is if we do evens and we do odds, right? And I guess I set this the other way. So this would be, we had even. So if even is set to 0 or 1, and if the bottom bit is either set to 0 or 1, right? So this right here is the address that we're writing to, or sorry, the line number, right? The row number, I guess we'll call it. This is our row. So if the row number is actually even, right? So it's 0, 2, 4, 6, right? So this is an even row, right? Then we want to advance only here, right? We don't advance here. If it was an odd row, then we would want to leave it, or we would advance here. So really what I wanted to show here, right, was that what we wanted to do was say if the value passed in for even matches the value of that bottom bit, then we do it, right? So it's basically like it's in equals here. It's saying, you know, if even equals true, right? Right? If even is true, then we want to well, it's actually the other way around. So I guess we do want this to be odd, right? I want to be able to make it do this, right? I want to be able to make it be this. I want to basically say, or I guess I could say not even, which would also guarantee that it would convert it to a 0 or 1 for me. So that might be fine. So if not even equals the actual mod value of this thing, right, the actual bottom bit, we could also say and 1, right, whatever that bottom bit is of the row, then we need to advance it. So that should be more what I wanted. Okay, so now what I wanted to do, draw a rectangle quickly, is we should be able to see quickly this flip back and forth, right? In theory. And it still does not seem to be doing it. What is going on here? All right. What is the problem, people? Oh, yeah, well, boy, I think so many things that I forgot to think about in that step. I did forget one obvious thing, which is that we're not pre-stepping the texture properly, right? P index, floor, test P. So first of all, you can't do it there. You've got to do it after we clip, right? Like so. So that has to happen. That's still not doing it after we clip. So there's all of our processing for that. So we got to do that. So that way it'll happen after the clipping. And then where do we pre-step the texture? Row equals buffer memory, row advanced texture memory. Okay, so those are just, we don't have to pre-step texture anymore because those are used in V's. All right. So that was probably why we were yeah, okay. So now we look like what I thought we should look like. So it's just because I was doing that in the wrong place stupidly. So there we go. And now, hopefully, when I do my switch, it'll actually work the way I wanted it to, which is that we should see the other rows. There we go. So that's what I actually wanted. So now that's good. All right. So now we're drawing every other row, right? Which means that I feel like I should be able to do this, where I can draw twice in a row with the two separate ones. And you can see that I get out the full composite result, right? So that's good. Our cycle counts are wrong now, so I should probably fix that so that we don't make a mistake. So in draw rectangle quickly, we, in order to not actually have to time through the loop so that we wouldn't affect things negatively, this value, this is actually wrong now. So we're actually doing half of these, right? So that's the way that goes, right? And there's also another thing here, which is that if the ymin, well, I'll do, since it's not super expensive, I'll do it up here. I'll also do if ymin, do we loop through to the thing? Equal to ymax. So if in here ymin was actually greater than, I mean, the only thing I'm worried about here is basically if that pre-step movement actually were to move ymin to be greater than ymax, this would miscount. I want to put it to do here. Clamp counters, right? We want to clamp our counter add. In fact, I'm going to put that. I'm going to put that actually in the let's see here, Handmade platform. I'm going to put that in the actual block counter stuff. Because if the clamp counter is so that if a calc, let's say clamp end time block counted, so that if the calc is wrong, it won't overflow. The other thing we can do here is people were asking on the forums for this, just to give them an easier time of compiling on other platforms. I think they were saying doing the RDTSC, they were asking if we could make the intrinsic stuff different. They were saying that basically x86 intrin was what was necessary. I don't know if maybe we can do that on all the platforms. No, I guess not. So, we could do something like this for them and hope that that works. I don't know if it will. But that'll give them something to play with, first of all, and they can do it. Oh, and I guess we could do this. Here we go. We could even do something like this. We could issue an error, right? Is that the right way to do it? let's see here. It might be a pragma error. Preprocessor error. Pound error directive. So if we want to emit an error, we can do it this way, like you can see. So we could say that if none of these were here, it's like, you know, SSE neon optimizations are not available for this platform yet. Compiler, just so it knows. Okay, so not that we have neon optimizations for anything, but still. So yeah, now that we've got that and we've got our counter working properly now, now we've got it so that we can do every other line, which is good. And so the other thing I'd like to do is make it so that we can properly do the frame buffer split up in those ways as well. So in order to do that, what I need to do is I need to make it so that when we draw the bitmap, the clipping is not based on the buffer, but on something else. So inside Draw Rectangle Quickly, you can see here how we do this, right? It sets xmin, xmax, ymin, and ymax to these 4 values. All we would have to do if we want to clip to a smaller rectangle is set those to different things, right? In fact, I shouldn't have shrunk the window. I shouldn't have expanded the window up because we can see right here the results of it, right? So if I want to, I can switch over. I can say, oh, you know what? Oh, well, so actually, this is the inverse. So this finds the rectangle. So it's, sorry, it's this part right here, right? Here's where we do our clamping. So if I wanted to, I can just introduce here some new values, right? Which is like, you know, like say our clip xmin, clip ymin, like so, clip xmax, clip ymax. And I can just put those in here instead of the other values, right? So I can just do, this is going to be clip xmin and clip ymin, that, clip xmin, clip xmax, clip ymax, there we go. So if I put that in there, now we should get basically the exact same result if I run it, so that's good. And you can see that it's doing the exact same thing. But now what I can do is say, oh, you know, I really didn't want to do the upper corner or whatever, right? And you can see that now we're only doing this one region of the screen. And I can say, oh, yeah, like really, I just only want to do this one 256, this one 128 by 128 chunk, right? And now it's only rendering that piece, right? Which is what we wanted. Pretty straightforward, right? Pretty simple stuff. So that's good. The only thing, I'm a little weirded out by the edge motion there, because I'm not sure why that edge should be moving. That should not be happening. I don't like that. Why are we getting that behavior? We're doing our clipping, and we're doing our even odd, which is fine, because that has nothing to do with it. But why are we not filling the entire rectangle every time? Because we should basically have everything that wants to fill in there should be filling in there. I don't understand why that's the case. It's like our stepping over xmax is not quite correct. I'm not sure what's going on there. I am not sure. So let me take a look here. Want something that will... Yeah, so you can kind of see. So I feel like what's happening here is we're being too conservative on like the right-hand side clipping. right? It's like, it's not actually always doing the right number of things. Now, okay, so I think I get what's going on here. So, okay, no, that actually makes perfect sense. So what's happening here is just that since we're writing by 4 pixels every time, but we're not actually writing by 4 pixels aligned to where the clip buffer starts, it's wherever the texture starts, we'll go over by that many. However many the alignment is off. That's interesting. So what that suggests to me is that either, because we'll want this to line up properly, right? We don't want, once we break these up into chunks and assign them to different cores, we don't want 2 cores writing into the same memory because they may overlap improperly, right? So we don't want to do that. We want them to be perfectly clipped. So either, if we want to continue doing this unaligned, right, then what we would need to do is when we get to the end, right, and we'd probably align to the end and do it at the beginning. We'd probably do the first time through the loop. We would preload the first time through the loop. We'd preload the mask for writing to be something you and in where it's got those first few pixels masked out so that it doesn't write them. That's what we would probably do there. But the question is, do we just want to always write aligned anyway, right? That's the other question. Do we just want to try and always write aligned because maybe aligned writes would be faster? And we don't know because we haven't tried that. So what we can do is we could do a quick test to see. Right, here we are running around. It's all a bundle of fun. You can see it happening here. Okay. Why is our count wrong now? Did I miss something? Our count is now totally bogus. How did our count get busted? You see what I'm looking at, right? Why are we getting 1 cycle per pixel all of a sudden? What's going on there? I don't understand. There's no way to get 1 cycle per pixel. That's not even theoretically possible. So that's just a bogus value. But I don't actually know why we're getting said bogus value. Because this is still the right number, right, that we're passing. We're passing in half the y span, x span minus x, yeah, right? And we're just dividing by 2 the number that we're submitting for process pixel. And it was working. I mean, it worked properly when we did it before. So like something is busted now where our counts are totally erroneous, which I don't get. So I suppose that is well, you know what that probably is? It's probably exactly the thing that I said it was. It's probably that when this thing gets clipped, the ymin and the ymax, this actually becomes like a negative number, and then this goes backwards. Let's go ahead and find out if that's the case. You know what I just realized? I realized something else. Man, there's so many things. I think normally when I only stream for an hour, things are kind of compressed. I'm thinking about all these things in the code now because I'm like in the code for long enough. You know what else I just realized? We were running our assertions when we were looking at the code. Like until I replaced those fetches, the assertions were actually in there, right? Because we didn't actually take out our assertions, did we? Like handmade internal and handmade slow are still set, right? All we were doing is flipping O2. So basically the assertions that were on the fetches were still in there. And somehow, because they were basically branches that never actually occurred, I guess, somehow they were never costing us anything. Or the compiler somehow magically was able to figure out that it couldn't possibly happen because of the min-max. I don't even know. But that was kind of weird. All right, well, doesn't really matter. Point being, what I want to do here is an end time block counted for a second. I want to go ahead and see if what I just said is actually the case, but I suspect that it is. In fact, I can just go ahead and do it in here. Let's go ahead and do build.bat, and I'll do O2D. And here we go. So when I step into here, or not, why are we not breakpointing? Hello? Hello, Mr. Code. I would like you to breakpoint. Oh, is that the wrong? That's draw rectangle slowly. All right. My bad. Draw rectangle slowly. Here we go. So if we step in here, I assume that's what I will find. Go to disassembly. Is that this value is actually wrong, right? Like this value is actually getting to be negative. So let's actually find out if that is the case. So there's the moles, and let's see, we have to do, where does it actually increment this value? Let's take a look here. So that is in our debug counters, right? So this is in global memory. What's that actually called? Global game memory? Debug global memory. So that's in debug global memory. Here's our counters. Here's the actual cycle count that we're looking for there, I guess. Right, because it's number 3 is the one we're talking about. So as we come through here, that one actually worked. But the hit count, so the hit count's what we're looking for. It's at 66924. Yeah, so it's just incrementing the cycle count, but the hit count is bogus. The only thing is that should... no, I bet... So if those are uint32s, probably it just becomes very large negative at some point and wraps around or something like that. You can see it happening. See the hit count going down? So the hit count probably keeps going down because it produces a negative number because it overflows. The negative number, yeah, then probably wraps the hit count around until it's, goes down below 0. You can see it going down, right? Goes down below 0, and then it's a huge value. Ah, crap. Didn't mean to type a key there. I wish you could tell that Visual Studio, like, I would absolutely love a way to say, do not let me edit any code in here. I never edit any code, just only show me the code. So what we need to do in here is we need to just have a thing that that's wise about that, right? Not sure how we exactly want to do that, but I will probably want to do it in here so we can actually do something like, pixel count, and here is the pixel count, right? And what I'll do is I'll just wrap it in an if. So if xmax is greater than or equal to xmin and ymax is greater than or equal to ymin, then do it. Pixel count. Thank you, compiler, for catching that. So now we shouldn't be having this ridiculous negativeness, and hopefully we can get our cycle count back. That's good. That's what our debug cycle count should look like. And if we turn on O2, we should see it back down in the 30 to 40 range like it was supposed to be. Yeah. All right. Okay. So that's what we want, and that's a good thing. So now what we want to do is we pretty much want to just be able to pass that in, and then we're pretty much done. And the renderer, we can multi-thread it. We can start multi-threading on a Monday. The renderer will have the ability to sort of spam those things out to different places, right? So draw a rectangle quickly. It takes that clipping. It will need to get this passed into it. And then we need to go figure out what we want to do with that alignment stuff, right? Maybe we'll do that tonight too. We're kind of going for it. You know, sometimes you got to go for it. I don't know how long we've been programming now, 2 hours maybe. So let's see. So we've got these guys here. They do the clipping. So we just need to make sure that this can be passed in. We don't have right now a rectangle structure that's in integer space, which might be kind of nice because that's kind of what we're doing here, right? You know, if we had a rectangle 2i that was basically like a, you know, just something that worked like this, where it was like, you know, this sort of thing. It might be easier for us to deal with because then we could kind of pass these around and not have to have so many different things here. And we could also just make a thing that does clipping with them so that, like, you know, we don't have to repeat this kind of code all the time. Would also be kind of nice. Just so there's some stuff like that that's kind of just, I don't know. It's just, it's handy, let's say. So maybe we want to do that, and maybe we want to do something like this, like clip rect, you know? And so we do this, and replace these guys. And then what that would look like is that's just like, you know, clip rect min x, clip rect min y, clip rect max x, clip rect max y. Same here. Min x, min y, max x, max y. There we go. And off we go with our little rectangle. And then what we want to do is we just want to make that into an actual thing, right? I don't know where I'm going to put that, actually. Maybe down here. Okay. So I want to grab this, and I want to put this in here, and I want to do something where I can basically say, like, all right, you know, rectangle 2i, you know, intersect. So I can get the intersection of two of these rectangles, right? And I can do something where I intersect one rectangle 2i with another rectangle 2i, and it'll do that computation, this thing here, you know? Just seems like a good thing to do. So what I want to do is I want to do this now where I just say, you know, A x, y, and then this is like B, right? And then, you know, I guess this is really a result kind of thing. So I can say result min x equals result min y equals result max x equals result max y equals, and I can just look at whichever one of these is greater. So to produce the new min, what I want to do here is I want to be able to pick whichever one I want. Okay. So in this case, so we basically, if we're talking about rectangles, right, we've got two fundamental operations that we might want to do that are basically the exact same with just one thing flipped, right? We'll come back to that in 1 second, right? So if I have a rectangle and some other rectangle, there's two things I might want to produce. I might want to produce the enclosing rectangle, right? So if this is A and this is B, I might want to produce this rectangle here, and that's the union operation, right? That unify, that like makes something that that is the combination of the two maximally. It encloses all of the area of both of them and some extra area potentially. Or I might want their overlap, right? This part right here. And that's the intersection. For clipping, what we typically want is the intersection, because we have like a screen or an area of a screen and then a sprite or something, and we want to know what part we need to actually operate on, where are they both. But other times we might want to do other operations where we're trying to do stuff where we want to know, like, oh, I have to process something and I want to process it only once, but it needs to cover the entire area of like two different sprites. I might want to union them together or something, right? And so what you can see is really all these two operations are either taking the minimal or maximal versions of each of the components. So like, here's the min x of A, and here's the min x of B. If I want the union of them, I want whichever one is less, right? So if this were the union operation, right? If I'm doing union, I want whichever one of these is going to be less. So if A has the lesser min x, right? Then that's the one that I want for the union. Let me actually do this here. If the min x, what am I saying here? Let's see. This is the min y. This is the max x and the max y. There we go. Let's try this one more time. Let's try that one more time. All right. So if A has the lesser min x, then we're going to take it, right? I'm sorry. That's A. If A had the lesser min x, we're going to take it. If B has the lesser, no, I was right the first time. That's B's. This is A's. So whichever one has the lesser min x, we're going to take it. A has the lesser min x, we're going to take that. If B had the lesser min x, like it was out here, we would take that to produce the union. So whichever one's less, we would take. Similarly, the min y, the max, we want to take whichever one's higher, right? We want to take whichever one would enclose the most amount of area. And so that's what we did here as well, right? If the max x is greater, if the max x is greater, we take that, otherwise not. Now for the intersection, we want to do the exact opposite, right? We want to take whichever one of these values is actually going to be greater, right? So if the min x, we take the two min x's, we want to produce whoever is going to be higher, so that we use the least, we want to take the least amount of area, because we want to make sure we start on whoever would start last, not whoever would start first, right? And so really all we're doing here is we're doing the exact same thing, only with the sense changed around, right? We're just picking the opposite person's thing based on which is going on, right? So those are those two operations, right? So now if we take a look at what's happening here, you can basically see that what we were doing here is saying, well, okay, we want to do the intersection here, so we were saying whoever's one is less, we'll take it. We know that x min is already set to something in particular, so we're just going to say if clip rect min x's was going to be higher than it, right? We want to take that, because it's the intersection. So we want to take whoever was higher. And so here's our intersection, right? This takes whoever was higher. B was higher in this case, in the intersection case. If we were doing the union and grabbing the whole thing, we would have done it the other way around. So yeah. So you can imagine that doing that this way, where we have the fill rect, right? And the fill rect is x min, x max, y max, like so, right? You can then imagine us doing rectangle 2, or just fill rect equals intersect, clip rect, fill rect. And that would just give us that intersection of them. And then obviously at the moment, since we're not using the rectangles through the pipe, although I guess we could now, right? So now we could. Let's just go ahead and take x min everywhere that it occurs, right? You can see where x min occurs here. We could just go ahead and replace all of those with the fill rect version. So let's go ahead and replace x min with fill rect dot min x. Right? Let's go ahead and replace, where are we here? Where's my fill rect? There it is. Let's go ahead and replace y min with fill rect min y. Oops, didn't quite mean to do it there. We haven't gotten there yet. So let's go ahead and replace y min, oops, y min with fill rect min y. There we go. X max, same thing. Replace x max with fill rect max x. And then finally, we would want to do, let's see, y max with fill rect max y. All right. So, oops, that's no good. So, now we've got it working off of the rectangle, which is good. And if I go into there and I take a look at what's going on here, I can say, well, we're doing all this with the fill rect stuff. We could actually do a couple other things here. Oh, we've got a to-do remove this too. Let's do that tonight too, before we go anywhere else. So what I could do too is I've got down here, right, I want to get the area of this thing. I could make that a thing to get the pixel count, right? I could do something where I just divide by 2 whatever is the get rect area, get clamped rect area, you know, so it's not going to be below 0 basically, and just pass the fill rect, and that would be this value, right? So then inside Handmade Math, I can have in here a thing that's just get clamped rect area, and that produces a uint32 because it cannot be negative, let's say. Although I don't know, I think we probably want to stay in int32 for everything. It'll still be clamped, but we just won't actually do that. And so then in here, what we can do is we can actually just do, in fact, we can just do it this way. We can just do result equals yes, A, and we don't do the divide by 2 because that's specific to that particular routine out there. So there we go. So Amax, yep, that's all good. And then we go ahead and take the pixel count is actually the result now. All we have to do is say if the result is less than 0, the result equals 0, and then we return the result. So there we go. Now, there is a sort of problematic thing here that I'm going to point out, and I don't know how we want to handle it. But our convention for rectangles before was that they did not include their final value, right? In fact, I'm pretty sure we said that so that they could overlap properly, right? Not sure where we actually talked about that, but if you look at the min-max here, if you look at the operations on the rectangles, we essentially had rectangle operations that would do like overlap tests, and the overlap tests always used less than on the final pixel, right? You can see that happening. So it's kind of broken for us to introduce this other, you know, just because we're doing some slightly different thing with the integer rectangles, it's kind of messed up in a way to have that one not work that way. So I do wonder if we want to make that work slightly differently where, you know, we can just sort of rewrite this routine to actually have it so that it does not work that way. It still considers that final one not there. And then we would get rid of like these +1s and all of this stuff would actually use the maxes and so on. So it feels like that's probably the right thing to do. So I'm going to go ahead and try it. And if we hit some reason why we don't want to do that, then we can not do that, right? That seems like a good idea. Now, inv with max here, we're not using those in this routine, are we? Yeah, I didn't think so. Those were for the lighting stuff. So I'm going to get rid of those in here. There we go. And we have these to-dos too here, like we haven't actually finished with the row alignment and stuff like that either. So there's stuff like that we have to do. Fixed cast Y. I don't know. This stuff is not used anymore in this routine. All right. So what we want to do here is change this around so that we're actually not assuming that the max is actually in anymore. And so in order to do that properly, that's actually not that hard, right? I mean, basically all we're doing here is treating these values like that instead, and that's it. So that's really not all that interesting. How is this min x? That was pretty funny. We changed that one over. Oh, well, anyway, doesn't matter. We'll take care of that in a second. So if we got these two, the width and the height here, and we start treating them this way, we come through here, and when we're actually doing this, the key here is just that now, when we're actually testing these guys, we need to test them. You know, that's gonna drive me nuts. So I'm gonna have to change that just temporarily. That would drive me insane if just that one is written that way. It's a little OCD there, but what are you gonna do? So the problem here is now when we come through here, everything else will work fine, right? Everything else that comes in here is actually pretty straightforward because everything else that we did in here, really the only difference, right, is that this would happen. That's it, right? We wouldn't work on that last guy. That's all there is. So that's pretty straightforward, and you know these become this way, and then and that's it. So it's really not particularly difficult to change. The only thing that actually has to change, that I'm thinking of at the moment anyway, is this thing right here that produces the extents. Because what happens is this thing doesn't actually consider that it assumes that it's going to touch that last pixel, the CLX pixel here, and of course it's not. That's not actually going to do that. So let's take a look at this for a second. It floors X and then ceilings X, so that's fine. So if floor X is and ceiling X is, all we would really have to do is make sure that the ceiling is incremented by 1. I think that's really all we'd have to do. Oops, that's the floor. I think that's it. I don't think there'd be anything else, but don't quote me on that. So that looks pretty reasonable. That looks pretty okay to me. So we'll go ahead and clip that out. All right. So what's going on here? Min x times max y result. Result equals 0. Result. Okay. So what is actually, although what's happening here? I have gone and broken it again. Check it out. We're back down to 0 cycles. I don't know how I keep breaking this. That's kind of absurd when you think about it. I shouldn't have this much trouble keeping that working, but apparently I do. I do not know why. Let's take a look and see. Clamped platform. So we pass the count in here, right? And we add the count, the count to it. You know what I could do here also is just quickly do assert count greater than or equal to 0. Okay, so that does not seem to be the problem. There we go. So yeah, so for some reason, we're not getting the right value out of here because the hit count is drastically higher than the cycle count that we're taking. And so I'm not sure why that is happening. I do not understand why we were getting such a high hit rate there. So let's go ahead and take a look at what I messed up. Because let's not mince words here, people. I am the person who did it, right? I broke it. It was me. There's really no question about that. So come in here and let's take a look. Should be able to step into that. What's the result here? 845. So is that reasonable? min x, max x. Oh, no! No! So this was totally, yes, that's totally wrong. I tried to take a shortcut there, but that's totally wrong. So if both of these are negative, they'll multiply into a positive. So you can't actually, right? You can't cheat. I tried to cheat, and you see what happens to cheaters, right? They get punished. It's not actually true. In the real world, most of the time, cheaters do just fine. It's what we call the financial services industry. In America, I don't know, and also in London, I don't know if you guys have that wherever you're listening out there, if you guys also have people who primarily make their money by cheating. So if we go in here, we need now to say, we need to make sure that our width and our height are both greater than 0, and then, and only then, can we actually multiply them together and actually produce the result for the rectangle area. Okay. So that should, hopefully, maybe, if we're lucky, that should potentially give us, well, I don't know what it'll give us, but hopefully it'll give us something correctly. Yeah, that looks like the correct debug cycle count again. And let's see if we can get our reasonable O2 cycle count again. Again, yes, does look okay. So, all right, so we're not too messed up. Okay, so now that we've done that and changed that into something that's a little more systemized there, we've got our rect stuff going. We can go ahead and hoist this up a little bit further, potentially, right? And so what I could do is I could say, you know, we've got this clip rect and this fill rect. We could basically what this routine is doing, right? What this loop is doing is it's just trying to go through and it's trying to take each individual point of the 4 corners of our potentially rotated texture map that we're, our potentially rotated quad that we're texture mapping. And it's trying to make sure that it gets the min and max bounds of those. So in order to do it that way, if we want to keep doing it that way, which is fine. I mean, this is probably not going to be a critical part of the performance of the application or anything. If we want to keep doing it that way, what we could do is just have a thing that's like expand rectangle to include point or something, right? And we could say that we would like our fill rect to be expanded to include floor X, floor Y, right? And we would like it to include seal X and seal Y, right? And we could do it that way. The downside of doing that is that we lose the fact that we know that we only care about the sidedness of it. So I don't know if we really want to do it that way. It's a little weird, to say the least. What we could do at the very least is loft this up one higher. So do something like this. And just access the things out of this. So now we're just doing basically width max, height max, 0, 0, something, right? And we get rid of these guys altogether. So we could do that. That's not too big of a deal. It's not actually doing anything useful at all. Oops. Right. So yeah. Now we do have one more thing we have to check, unfortunately. This is one of those things that, I wish we didn't have to check, but we've seen it already happen once before, and so I got to do it just to make sure. But let's go ahead and do this now. There we go. And again, the reason I'm doing this is just so we can reuse this code a little more easily, because we're going to have to clip everything. Like, we're going to have to clip all the different functions that we do. They'll have to clip to this, all the rendering functions. So we need to make sure that we add clipping for our rectangle outlines and all that sort of stuff, right? But so what I was saying is, what we need to check here is that putting these things in a structure doesn't confuse the optimizer, right? So what I'm going to do is I'm going to go ahead and just take a look at this, right? So you take a look at that, it's 43 cycles, right, or whatever per hit. And let's take a quick gander at it here as well. Do we still have that on? No. It's cool. It looks like we can just leave that on, and somehow it doesn't actually bother the runtime of the thing either, at the moment anyway. So yeah, so we're doing that, and that's all good. But I also wanted to kind of see what it was here if we take the count of it, right? 116, 95, so 117 cycles, right? And so I just wanted to see if we have any, so if it confused the compiler. So I just wanted to see if we took out any accessing of fillrect from the actual loop, right? Meaning this code right here. I just wanted to make sure that went away, right? So that if I took this out, it didn't actually affect the runtime performance in any particular way, right? So min y equals fillrect y min. Oh, I don't know why. I was in the habit of reversing those. There we go. So I just want to see if that has any adverse effects, basically. Doesn't look like it does on the runtime there. And it does, oh well, it definitely had an adverse effect on the runtime. I mean, not the actual runtime, but it confused the compiler. The fact that because it was 117 before, and it's 113 now. So unfortunately, it does look like we'll have to, even if we sort of pull out the reusable code at the front end into some useful structs, I don't know that we'll actually be able to access them directly because it looks like it's confused about that. Even though it's just a stacked variable, it looks like it got confused. All right. Okay, so a couple other things we could do here. We have a remove this. And I'm assuming that the reason that we have a remove this is because this pixel px thing we could just keep as a wide value and increment it every time. At least I'm assuming that's what I meant by remove this. But yeah. So it also looks like origin x4x. So we could just roll all this in, right? So instead of using min-x at all, what we could do here is just say, all right, we've got a M128. The M128 is called pixel px, right? And pixel px doesn't get modified in the loop anywhere, right? It just gets incremented this way. Oh, wait, oh, okay, so it does. Never mind. So what we need to do here is we need to introduce a new thing, which is like pixel px for the row. And that's just going to be set to whatever that y min is, right? So basically, I'm sorry, whatever that min x is in this way. So we're going to do this once still to get it initialized to what we were actually starting with as a value, right? So we're going to do that. And because that's always going to be that first value. But then what we're going to do is every time through here, we don't actually need to well, actually, I guess we don't really need to do this at all, right? This is all just obvious stuff. The compiler probably already did this, I would hope, because it should have been pretty obvious, but just in case. So we can get rid of that because this is always initialized to the correct value. So really, we're just taking this and subbing out the origin, right? Like so. And really, we could have just subtracted the origin there. Do we ever even use origin x4x again? No. So really, we could just set this once, right? Something like this, I feel like. And then just get rid of origin 4x entirely for the moment. Because unless we decide to do the whole preamble in SymBD at some point, which we could decide to do, but it probably isn't necessarily worth it, there's just no point in even doing that wide because we only do that there. And that's it, right? That's the end of that. So that's fine. Pixel PY, we could also do that way. I don't know if it's useful to do it that way, but we absolutely could. I also don't know why on earth we were doing this as a sub PS. That's just ridiculous, because if you're already doing this as a set Y, I don't know why you wouldn't just do it this way. Again, more ridiculousness in our loop. But yeah, so we can take a look at that in a second. So there we go. Let's take a quick look. 117 cycles. So how did that go back up? What did we do that made that go back up? So I guess saving this register was actually worse than setting it every time, right? I mean, that's what that appears to be the case. Am I wrong about that? Like, it looks like setting that, having it have to remember that register was actually bad. It would rather have just used this value, which I guess it already needed to have, right? And go from there. That's what it looked like. I don't know, but that's what it looked like. So if that's the case, that's fine. You know, we don't have to argue about it. We can just do it this way. And that's fine. So let's see if it prefers that. That didn't change it at all, which also doesn't make any sense. So how is this possible? Someone explain to me what is going on there. That is the compiler is just doing weird stuff at this point, I feel like, because why would that actually matter? That does not make any sense to me why that would matter. It just seems very strange. Very, very strange. I don't get it, people. I really don't. I don't understand why the compiler should not have been able to produce the exact same code, right? But it couldn't. It didn't. It had 113 cycles here, and then when you tried to do it the other way, it didn't. It couldn't do that, right? So that's pretty strange. So it really wants. It would prefer, right? It to look like this. That's what it would like to see, according to the minimum coming through here anyway, right? 113 cycles. So it would really like it to look like this. So we'll leave it like that. That's what we want. I'm not going to tell you. I'm not going to tell you what else you should do. Because remember, this part of the code is not even getting counted by this. So what that was meaning is that our critical the part of our loop that gets executed most often, rearranging what was happening here was causing it to have a problem doing the optimization, whatever optimization it was doing on pixel PY hoisting. Because presumably pixel PY, which is constant across the loop, right? Across the inner loop, it can hoist out these two mulls, right? It can do that. That's the only thing that pixel PY actually multiplies by, right? So it can hoist out those two mulls, but why hoisting out those two mulls was getting so much harder for it when I did it the other way, I'm not actually sure. So maybe we'll take a brief look at that just to see, right? We're getting that 113.20 cycles. Let me hoist that out and see what starts happening as I play with that. So this is, ppnx or pynx or something. I don't know what we're going to call that. And this is py and y. That's just those two values, right? So there's the x. There's the y. Pyn x, pyn y. And presumably now, literally all I've done is hoist out exactly what presumably the compiler was already hoisting out. And yes, so it stays the same. So that's what I would expect. And so now the question is, okay, pixel py, right, which is getting set once here. We do the mul. I don't understand. Okay, so let's say I just look at it like this, right? And here's that pixel py stuff. I check it out. I'm 113, 20 cycles. And now all I want to do is I don't want to just subtract origin.y in here. How bad is that? Right? How bad, how much do you dislike that? You dislike it quite a bit. You dislike it by 3 cycles. So you really don't want to have to do that. You want to do this for some reason. I don't know the reason, but for some reason. Okay. So the y value is only used in this loop in that one place. So how about I try a different tact, and I just ask you to go between these two values. Like so, right? Let's say I was to do that. So I'm going to go ahead and say that these actual values here are going to be this way, right? Because that'll still loop over the same actual pixels, because I'm not changing the actual pointer. It'll still do the same number of iterations, but the multiply has been folded in, right? Does that make some sense? And so then we just eliminate this altogether. We're just doing a set 1 PS. That's it. Oh, I can't quite do that, can I? Because that's a floating point value. That's why, right? Because we're trying to compute the texture coordinates there. Well, wait, what's it complaining about? Oh, sorry, didn't mean to leave that in there. Well, I mean, I could try to loop over a floating point value. I don't know if I love that idea, though. Right? I mean, yeah, hard to say. Wait. How do we go back to 116? How do we go back? How do we just go backwards, people? What happened? How did that happen? I didn't do anything. This is the way we had it before, right? Before I did anything. That's what it was, right? What? That's the same code. That was like exactly the same code. Okay. I'm very interested to know, Mr. Fancy Pants here, what was the typo? Or the slight change that caused the compiler to not do it that way? All right, we've got texture memory, we've got the fills, we've got the process pixel, x, y, pixel py equals set 1, origin y 4x. What's the difference? Oh, that's the problem. Okay. Okay. It was just because since I had not allowed the actual guide to complete, it was just holding the DLL open, so it didn't rewrite it. Okay. That's fine. I thought I was going crazy there for a second. But basically what happens is when I had it open like I did the more, this is holding the DLL open for some reason this guy doesn't close the DLL after it's done with the analysis and it's printing it out. So that's fine. It would be nice if that weren't the case, but it is the case, so that's what we're going to do. I could do it like this, I suppose, wtemp.out, and then try to do a more on temp.out. I don't know if that'll work. Oops. There we go. So let's try that. Actually, I should probably do it temp.out. Like so. Okay, so let's see if that works. So if I hold that open now and I compile, I should be fine. Yeah. So just going to an intermediate file is fine. That's totally fine. Let me delete that though. I didn't mean to put one. I didn't mean to put a temp.out in the root directory there. So that's fine. And I'd like to capture that. This should just be a line that we do, basically. That should just be a bin, because we're going to want to do that periodically. So what I'm going to do is I'm going to throw that into the mist directory. And I'm going to go ahead and make that in here where we do like, you know, where we do a like, call it nhm.bat. We'll do the Nehalem, right? And so what that's going to do is that's going to, I don't know where we'll actually run it. So I guess we'll maybe just leave it like that for now. Yeah. So this way, if I just go nhm, I get it, and it's good. I can just do that anytime I want. All right, let's leave that like that for now. Think about how that should go later. Okay, so if I do all that, kind of surprising. Doesn't look like there's a whole lot of ways we can do anything that doesn't make the compiler feel worse, really, about what it's doing than what it's doing already. So that's just, excuse me. That's just the way it goes, I guess. So I think we may be down to just thinking about that alignment problem. And so the alignment is basically, let's just go over this real briefly. We talked about it a little bit, but alignment just means that when we're writing the stuff, you know we've got these 128-bit wide vectors, right? Hello, mischief. Wake up. Okay. So we've got these 128-bit wide registers, right? And inside them we've got 4 pixels. Here's pixel 0, here's pixel 1, pixel 2, pixel 3, and we're writing these out to memory. And right now what we're doing is we're writing them unaligned, which means that if you imagine memory was broken up starting from byte 0, right? If you imagine it was broken up into bytes, you would basically have every 128 bits, starting from the very beginning of memory, starting every 128 bits, you would essentially have a chunk. So here's 8 bits, 8 bits, 8 bits, 8, right? Like here we go, 8, 8, 8, 8, 8, 8, 8, 8, 8, 8, 8, 8, and here is a 128 bit boundary, right? Or 16 bytes boundary. And then we go again, 8, 8, 8, 8, and there's a boundary. So these boundaries are absolute in memory space. It doesn't care where you think things start. They're literally absolute. So if you were to take a look at the pointer value, right? The pointer value is going to be something like, okay, so this is we're never going to get a pointer here because low memory is not mapped in this way ever, because you know the null address is 0, right? But let's say you had a pointer with a value of 7, right? So that's the 7th byte, right? Here's 0, 1, 2, 3, 4, 5, 6, 7. I should say it's the 8th byte, right? Numerically. So we're pointing into here. So the question is, if I was going to do 128 bits of writing, right? 16 bytes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I'm going to write that. What you can see is this is unaligned in the sense that some portion of the write that will occur happens in one of these buckets that is broken up absolutely, and the rest of the write happens in the next bucket. So we've got two essential, you know, anytime we do 128-bit write, there's only 2 ways that can really happen. One way is we're perfectly in only one bucket. So we start on byte 0, byte 16, or something mod 16. We start right there so that we write entirely into one bucket. Or we straddle 2 buckets is the other way. Now we can't ever straddle 3 buckets because the buckets are the same size as the write, so we can't possibly get more than 2 buckets. But we can get either 1 or 2 buckets that we have to touch. And the processors, depending on which processor you're talking about, like these more or less. Meaning, sometimes the processor doesn't really care if you write things underlined. Right? In the old days, that really certainly wasn't anything anyone thought about. Because processors could only write things at one size, and things could only write a byte. There was no such thing as being unaligned on the byte, right, or whatever. But when things go out to starting to work on 4 bytes, like 32 bits, there were processors that were like, okay, if the 32 bits happens to be aligned on a 32-bit boundary, 4 bytes, right? It could go a little faster, let's say, because it doesn't have to think about it as much, maybe, or whatever. The processor is working with 32 bits at a time. It was easier for it if they all kind of slotted in together or something. And that's been true all throughout history since then. You pretty much had this case where as the processor deals with wider and wider stuff, some processors have an easier time dealing with operations that line up with memory along the boundaries of however wide those values are. And that's the situation that we want to investigate now, is this particular situation. Now, in some processors, it's extraordinarily important. On other processors, it's not so important. And so it's always kind of a balancing act that you do there. So the first thing we can do to test this, right, is we could just align our xmins so that and xmaxes so that we're always aligned, basically, right? So what we could do is we could say, we've got this row pointer here, right? We could just cheat for a second and say, let's pretend we were always aligned. So let's look at this guy here. And we'll look at this is a pretty janky way of doing this, but I'm just going to do it briefly. So it's running at 38 cycles right now, right? Let me just run it. Let's run it without the clipping too, because we want a bigger test case here. So our clip rect is just going to be, the whole screen. All right. So there we go. There's the guy. We'll just do it straightforward here, 36, 37 cycles, right? You can see that's what we're getting. So if we come through here and we now say, all right, this row pointer, the place that we're going to be reading and writing from. Now remember, there's really not much we can do about alignment on textures, right? Because the textures, we're randomly accessing stuff right straight out of them. There's not a whole lot we can do about aligning the textures other than trying to do something fancier about maybe the way the pixels are stored in them or something. I don't know. But point being, those are random access. But the frame buffer is not random access. So what we could do is say, oh, okay, let's pretend we were always doing aligned stuff here. So what we could do is say, all right, our alignment offset, so our align value, right, whatever that pointer is, we'll go ahead and grab that pointer. I think, do we have uint pointer? Do we have a uint pointer? Let's take a look. We do not. So we don't know what the pointer size is, unfortunately. We haven't actually done any work to get that. And I'm not sure I don't remember how you do that. C now has a newfangled way of you can get some of these things. So what I want to do is have a uint pointer. And I don't know, can I just Hail Mary it? No. So what is the pointer type? Let's find out. They've got to have done this, right? You wouldn't go ahead and do this stuff, I really hope, without putting that in there. So let's just assume that it has that. So there's, I thought I saw it. Yeah, int pointer. It's there. So how do I? There it is. There it is. Int pointer and uint pointer t. Well, wait a minute. That's what I just... Oh, I had it backwards. Sorry. Okay. So basically what that allows me to do is say, I want to change this to an integer that I can manipulate, but I want it's the same size as whatever the pointer is, right? So that way on a 64-bit build, it'll be 64 bits, and on a 32-bit build, it'll be 32 bits, since this is a pointer, right? So there we go. I get the pointer, I turn the pointer into a thing, and then I just want to look and see if it's 16-byte alignment that we're looking for, right? That's going to be 2 to the 4th. So what I want to do is I want to take 2 to the 4th, right, 16, and I want to just subtract 1 from it, right? Because that would give me all 1 bits below where the 16 is. So I can just look at what the bottom bits are of alignment, right? So that'll give me essentially however far off this thing is from being alignment, from being in alignment. And then I'm just going to go ahead and just flat out subtract that times bitmap bytes per pixel. I'm just going to flat out move the thing back. So this is a complete lie. It's not even going to render the right stuff. It's fully garbage, right? Oh dear. What have I done? I think I know why that happened, but I don't understand why the debugger crashes. It's supposed to be the debugger. Like, the debugger should not crash, people. God. Our program should crash. We are the one developing the program. You're supposed to be done developing your program, and it shouldn't crash. I don't feel like I should have to explain this to you, Microsoft. This is not complicated. Maybe if you spent less time installing SQL Server on my machine for your Visual Studio nonsense, and more time making sure that the debugger didn't crash when debugging a program, we wouldn't be in this situation. Anyway, point being, what I was trying to say was that in here, when I'm doing this alignment right, that could step back off the end of the bitmap. So in order to prevent that, I would have to sort of always clip to something that gives me, like, we could just have a whole row of padding even at the moment, right? To do stop padding by a row. This is much like what we're doing here for the padding. So that's fine. Yeah. You know what? I did this a stupid way too, didn't I, here? Because this, we probably could have... Well, no, never mind. Anyway, so point being, off we go. Hopefully that would stop it from crashing, because I think we would never fetch backwards too far at that point. But as you can see, right, it doesn't render things in the right place because I'm not doing any work after that. I'm just flat out forcing the alignment to be correct, even though the alignment is not correct, right? And so that's not good, obviously. But if I go ahead and do that, all I'm going to try and do here is see whether moving to alignment helps or not, right? And so if we take a look at what was happening here, right, and I take a look at that line, let's go ahead and take that out for a second, right? Here we are running 37 cycles, yeah. If I turn on alignment stepping, should stay the same roughly, I would assume. Well, it actually gets just a slight bit faster. And then what I wanted to do was I want to go in here and change our load and stores to no longer be unaligned. So you remember we were calling load U because pixel was not aligned, right? I can change load U to just a load, right? And we didn't have any other ones there. And so then we've also got the store U, which is unaligned, but let's change that to aligned. So now I'm just using the aligned versions of those guys, and that's it. What happened here? So I guess I did not do that alignment properly. Let's start with that. Oh. What? Yeah. Do not ask me what I was thinking there, first of all. I don't know why I thought I wanted to make that be that way. I didn't want to do that. I want to literally step it to the actual alignment. I don't want to multiply by a pixel value. This is how much it's off. So we're just going to do it that way. Yeah, that was pretty dumb. Anyway, so here's the version that's using store u and load u. And it doesn't look any different to me, right? The speed did not change at all there. So basically what that tells me, unless I've made some kind of an error, is that at least at this point, until we address potentially other memory issues, that alignment is doing it unaligned is not a problem. And furthermore, for all we know, even after we address other memories, that might still not be a problem. Meaning it's possible that the unalignedness of the store and the load, based on the fact that there's so much other work that we do, is just it just isn't relevant. And we'll always be better off doing it that way so that we don't have to overfill by more pixels, right? Because, yeah. So I think the alignment there does not really look to me like it's an issue at the moment. So we're pretty good there. All right. So we have one last thing that we probably want to do here in terms of stuff as we're fiddling with this routine. What we'd like to do is we would like to make sure that we actually always fill the real clip region and we don't write outside the clip region, right? And so the way that that's going to work is we know that we have to go over our pixels like so, right? We know that we have to do 4 pixels at a time. And so if we're doing 4 pixels at a time, we have to make sure that our mask doesn't allow us to write pixels that are outside of where we're trying to write them. So like on the last time through the loop, when we're going to write the final thing, we would need to make sure that our mask was set to not include those additional pixels. Now, the other way we could do it is we could make sure that it's aligned at the end, and it's the beginning that's going to be unaligned to 4. And I'm not sure which one we want to do there. Probably we want to align the end. And the reason that I say that probably we want to align the end is because I'm imagining that really the way we'd want to do this is to initialize the mask at the outset and then overwrite the mask with 0 at the end, right? So here's the write mask, you know what I mean? And so here's what I wanted to try and do. We are writing 4 pixels at a time. I drew that potentially a little bit large. We're writing 4 pixels at a time. There we go. So here are our pixels that we are going to write. And these are broken up into chunks of 4. So we have 2 options that we could do here for writing, right? Actually, I should probably make these line up as well. So let's just do it this way. So here's option 1. Here's option 2. So what we want to do, right, is we want to fill some region. We want to fill between here and here, let's say, right? So we want to fill 0, 1, 2, 3, 4. So there's 5 pixels to fill. But we know that we're going to fill them in chunks of 4. So we have 2 options here. We could either fill these and these, right? So here's pass, this is our first time through the loop. Here's our second time through the loop, right? And mask these out so that we don't write them. Or we can do the opposite alignment and try to write these out aligned to that ending edge and write these over instead. So here's 0 and here's 1. So the first time through the loop we don't write these, and in the other case in the last time through the loop we don't write these. So what I was saying is usually it's easier to start things up than to change them at the end, because what we can do is just initialize the mask to this, and then at the end of the loop clear the mask, so that we could never have to actually ever check to see which iteration of the loop we're on. It always does the same every time. Rather than having to go, are we at the end of the loop? 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 Right? It just seems simpler. So what I'd rather do is do it this way, where we start at the end, x max, and we back up x min to start here, right? So let's do that, right? Because we can see if I switch back on our clip rect, right? If I go in here and switch back on our clip rect, oops, that's not our clip rect. If I go back in here and switch back on our clip rect, and we can actually stop this now since we don't need that anymore. When we move around, you can see that we've got this bug here that I was talking about, right, where we overfill, because we're not doing anything to prevent that, right? What I want to do first is change it so that that error occurs on this side. That's what I'm going to do first, right? So what I want to do is I want to see that this edge firm up and this edge becomes wiggly. That's what we're looking for. So in order to do that, what I want to do here is come up with a different way of computing this. I want to go ahead and take sort of like the fill width, and that is going to be the max x minus the min x, right? That's the amount we're going to fill by. And then we're going to compute the max x and actually line that up with exactly where we want it to be. But then what we're going to do is the min x is actually going to be whatever that max x is minus the fill width, right? It's going to be minus however much we want to fill. And what I want to do is I want to round that fill width up so that it actually is based on chunks of 4, right? So again, we already sort of saw how to do this. So we have sort of our fill width, sort of our fill width alignment, if you will. We can take the fill width and we can AND it with 3, 4 minus 1, right? To find out how much it is off. And then what we can do is try to, we just need to compute the value that we would add to it to round it up to that value, right? And that's going to be whatever, assuming that this, if the fill width align, I could do this in a better way, but I'm getting a little tired at this point. It's getting late. I'll do this in the easiest way. So assuming there's fill width align is greater than 0, we would just take whatever it would be to add it up to 4, right? Hopefully that makes some sense. Oops, put in the fill rect there. Fill rect, right? So this is actually going to align that fill width for us, at least hopefully. That doesn't look right at all. What is the problem there? Fill with the line is however much we were off, assuming that we are off in some way. If it's exactly 4, we're fine. Then we're going to increase that fill width by... Next one is fill with the line. Well, I'm just going to step into it. Like I said, it's getting late, and I'm tired. So let's take a look. Fill width is here. Oh, all right, that's true. We do have negatives. So that's irrelevant for these, I guess. We want to look at non-negative values because only non-negative values are going to actually get filled. Is that just because of, we're in optimization mode? Let's turn optimizations off so we know we're actually looking at real values and not maybe potentially some mistakes. Okay. Let's see here. There we go. So we're going to fill something that's 48 wide, and that should be exactly, that's exactly a 4, right? That's a 12. And so fill width align should be 0. So when we back this thing up, we should see exactly the same values that were in the fill rec to begin with, right? And we do. So that's fine. So now let's take something that isn't aligned. Hopefully we'll get something 73. That's good. So it says that the fill width align is 1, which means that it's 1 off. Let's see if that's true. 18 times 4 is 72. That's correct. It's 1 off from, yeah, it's 1 over. So we want to add to it 4 minus the fill width align, minus fill width align, which is 3. So we're basically going to make the fill width snap up to the next largest 4 evenly, which is what we did. It's 76. And so now we're going to set up the places that we're iterating over, like so. Oh, yeah. So, I mean, it all looks correct, but again, just forgetting here, that only, right? That only actually does it before we've actually stepped to the location that we were going to step to, right? We have not actually set up the other values that we need here based on that adjustment. So that adjustment actually has to happen up earlier, right? I can't just do it at the end in this sort of nice, convenient way. That's not going to work because all the rest of our calculations based on that aren't getting redone, right? So that was just a little bit of stupidity, as happens. So we could just do that in here, right? Where we then say, okay, we'll take that fill rect, we'll take the min x, and we'll make that equal to the fill rect max x minus whatever that fill width is, right? And that'll do that. And of course, we only need to do that if we actually adjusted it. And there we go. In fact, I guess yeah, there we go. Because if we didn't adjust it, then we don't have to change it at all. So let's go ahead and check that out. See how we're doing there. And that looks a little bit better to me. You can see we're now solid on the right edge, but we've got like badness happening on the left edge, which is what we want. And so now what I'd like to do is I'd like to go ahead and actually do the clipping there. Since we already have a right mask, what I'm going to say is we'll introduce, this will add a little bit of a cost to our thing, but what I'd like to do is basically just take that right mask and add in the concept that we have to and it with yet, like one more thing, right? So when we do this and, right, when we do that, the and BS here, I want to do essentially like right mask equals and SI128. I want to do that on right mask and clip mask, right? And clip mask is just some value, clip mask, that we set to something here. And at the moment, I'll just do a set1 PS, or set1 API 32 to just make it be all 8s, right? Can you do this? Is that allowed? Apparently. Of course, it looks like, yeah, it looks like you have to set an integer 8. And of course, I can't actually set that. I could set it like that, I guess, which would, -1 is all Fs in the byte. So I could do that. But yeah, all right, well, let's see. So yeah, so now we're still getting the exact same result, which is what I wanted, just to make sure that that extra and is working okay. So it's set to all 1s. And so what I want to do is at the end of the routine, I want to set it to all 1s. So when we go to step to the next pixel, I want the clip mask to be set to all ones, certainly, because every other time through the loop, it's always going to write everything. And so then now all I need to do is set this clip mask to be like the startup clip mask, you know. And that startup clip mask is something that we're going to set based on this, right? So we have a 128i, which is our startup clip mask, okay? And by default, it'll be set to just, you know, not having to actually clip anything. But if we have to do an alignment adjustment here, then we essentially want to set that clip mask to something that will cause the clipping to work properly, right? So here is our adjustment, right? We know that we have to adjust by that much. And what that is that's essentially how many pixels we want to clip. So what that means is if you think about what's in our clip mask, our clip mask right now is set like this. It's got all ones in here, right? All ones, all ones, all ones, all ones, and these are 32-bit lanes. One for each pixel. So all we really want to do here is if we are going to align our pixels, if we're going to clip pixels, for every pixel we're going to clip, we want to clear out 32 bits of ones. We want to basically write zeros in there, right? So one pretty trivial way we could do it is take the number of pixels and shift down by 32 times that number, right? That'd be a trivial way to do it. I don't know if that's expensive or even possible in SSE. It's basically like a shuffle. It's like a, well, let's take a look. We'll see what we got. So what do we have for shifting and swizzling? Let's just take a look. Excuse me. So if we wanted to do that kind of a shift, that would be a shift. Left by an immediate. Let's take a look here. So shift A right by IMM 8 bytes while shifting in zeros and store the result in dest. So actually that would just do it. The throughput is quite fine for our purposes. So let's just do that. That looks fine to me. So we'll do, oh, and we don't even care here really, because now I think about it, this is startup code. Who cares? It hardly gets run ever at all. So our startup clip mask is going to be equal to the MM SRLI SI128 of the startup clip mask, and this is in bytes. So we basically want our adjustment times 4, right? We want to shift it that many over. Oh, nasty, but it's an immediate. All right. Well, is there anything we could do that doesn't need an immediate? Probably not. So what we probably have to do here is just do something cheesy like this. This is probably not the best way to do this. Just in case anyone was wondering. You know what? It's time for one of those comments. If the adjustment is 1, we need to go ahead and shift it by 1, 2, or 3. So off we go. Not quite right. It is shift right, correct? Because we want to clear out the top guys for the clip mask. I feel like. So for every one we add, we would want to clear out the top dudes of our clip mask. Yes? So I'm not sure why. I feel like that should be correct. But who knows? Let's go ahead and take a look. Okay. So come in here, startup clip mask. There's the startup clip mask. And in here we have our, see it in hex. We've got our dudes, first pixel, second pixel, third pixel, fourth pixel. And we come in here and we've got an adjustment to do. The adjustment is 1, fill width the line. Oh, that's a negative guy though, isn't it? So this guy won't actually be used, but that's okay. We can still take a look at what it does when it has to do an adjustment of 1. When it has to do adjustment of 1, it should get rid of this top top guy only, right? And it does. So that actually looks kind of correct to me. So I do wonder if maybe I've got something else wrong here. Let's take a look. Where's our like 73 dude? There we go. All right, so our 73 dude, he's got some bros to clear out here. He's got to clear out 12 bros, so he should only write the first pixel. So let's see what happens when we come down through here. Go, 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 go. What? Was the fill height nothing? The fill height was nothing. Great. All that, people, for nothing. Seriously. It's just absurd, really, when you think about it. So here we are in our clip mask. What's our startup clip mask look like? So here's another one where we've got that you know, we should really early out these guys. I mean, it's doing all this work on stuff that doesn't actually fit into the region at all. Let's go ahead and just do that, because that just seems a lot better. All right, so let's do this. Let's just take that pixel count here. It's not really pixel count. More appropriately, it should be called, well, you know what? I'll just leave this the way it is for a second. Okay. So what I want to do is at the earliest possible time, which would basically be here, I want to go ahead and just make sure that we're actually filling something, right? So I'm just going to go through here and say, you know, let's just early out the whole thing. And so for that, I'm just going to do like if has area fill rect. I'm just going to make a function in math.h, which is basically like inline bool 32 has area rectangle 2i, and this is just going to be equal to, you know, result a.min is less than a.max, and a.min is less than a.max. So we're basically just checking to make sure that in both cases it has extents on those axes, right? So that way we are not constantly going through a bunch of loops for no reason. And so now in here, our fill width should always be something valid. There we go. So we've got an adjustment of 2 here. We fill that up, right? There we go. We've got the 2 masked out there. Come down here. And now finally, we'll get to see this because I've actually ensured that we're going to be in things that actually go into the loop, which is nice. And so let's take a look at what we end up getting with that right mask and the clip mask. So the right mask, there's our right mask, and the clip mask. Oh, you know, and this is not because I'm on stream, just to be clear. I actually make these kind of mistakes all the time. Like, my brain just isn't solid enough on always keeping everything in the right order. I make these, I actually just, these are the kinds of mistakes that I make in like real life all the time. Like you saw me explicitly say, like it wasn't like I was confused. You saw me explicitly say I wanted to clear out the top guys, thinking that I wanted to clear out the later pixels, but it's at the beginning of the row. So you want to clear out the earlier pixels, right? I mean, that's just kind of obvious. So I don't know, like, yeah, I don't know why I have that problem, but I definitely do, and that always happens to me. So I was thinking of mentally what I wanted to do correctly, but mapping that to what actually happens in the register, I was totally wrong. So now it looks like we have much more solid clipping, right? So that's good. And I'll go ahead and turn on the optimized version, which presumably should not have broken much. It does cost us a little bit to do it, so that's unfortunate. But you know, we're going to need it if we want to break up stuff into chunks. So there we go, right? So now what I'd like to do, and this will actually probably hurt our frame rate, because obviously you wouldn't necessarily want to do this for any particular reason, but let's go ahead and and actually break this up a little bit. So instead of doing this stuff here, what I'm actually going to do is I'm actually going to start passing through that clip, those clip regions and stuff, right? So what I want to do is when we pass this stuff in here, to draw a rectangle quickly, oops, draw a rectangle quickly. What I want to do is I don't really want this guy to look at the buffer anymore. Like the buffer width and height are just not going to be relevant to it anymore. And so it's just going to use the buffer memory and pitch, and that's it, right? So it's going to take, in addition to what it's getting here, it's going to take a rectangle to I, which is the clip rect, and it's going to take an even or odd value, which is that parameter to say what is going on there. And then it is going to it's going to do this clip rect here. It's going to do this for initialization, like so. And then width max and height max should never be used ever again, right? Yeah. So, I gotta be honest with you, I'm not sure why we were subtracting 3 from the height before. That doesn't make a lot of sense, because we're writing by 4 things at a time, so it makes sense why we would need the width to not overwrite in that way, but why the height would have to be that way, I don't understand. So that's a bit odd, to say the very least. But that's the way it goes, I guess, sometimes. So let's get rid of that. And then we can make it work entirely off of the clip rect. But now we have to actually pass the clip rect in here. So here's our clip rect. And our clip rect, of course, is going to be this way, right? Width and outward target height. Now, this should crash, or at least have the potential to crash, I should say. And I'll talk about why in a second. It may not actually crash. What is happening? Something bad is happening. Something very bad is happening, but I don't know what it actually is. Whoa. We are like super slow right now. What happened? What did we do? What did we do? Something very bad happened, but I'm not exactly sure what it was. We are calling this twice now, but that can't really account for that ridiculous of a thing, right? Take that out of the equation, and that was still really bad, right? Like, that's just crazy slow. But I don't know why. I have no idea why we are so slow. Draw a rectangle quickly. It's still only taking 36 cycles per pixel, according to that. But I'm not sure how it was able to get so much slower like that. It doesn't make a whole lot of sense to me. I'm totally stumped by that, just to be clear. I have absolutely no idea why that would be the case. Well, I would like to go to bed soon, so this is definitely one of those bugs that we are going to have to think about how we can solve in short order. Because what on earth is going on there? Oh. That's funny. That is just stupid, as always. So yeah, this has to be inverted, right? Because this finds the area. So we were basically looping over the entire screen. It's kind of crazy that that's how fast that was. We were looping over the entire screen and touching every pixel for every single sprite. And it still ran that fast? That's pretty good. Man, we made this routine fast. That's pretty funny. Yeah, so this has to actually, this is not right. I'm going to go ahead and introduce the inverted infinity rectangle because everyone loves the inverted infinity rectangle. And what the inverted infinity rectangle is, right, is it's just an easy shorthand for saying I want the min to be equal to the maximum it could possibly be and the max to be equal to the minimum it could possibly be, so that when you do a loop like this, when you just go through it and you try to expand the bounds, it just works, right? So it's basically just saying, okay, I want you to produce for me something which is going to be the min x and the min y equal to int max, and the max x and the max y equals negative, right? Like so. Oops, in Lian, that's a good thing. There we go. Okay, so the inverted infinity rectangle hopefully will save our frame mate. I don't know if it actually will or not. We'll find out. And this is presumably the crash that I was mentioning. So temporarily, we'll sort of adjust our clip rect to make sure that doesn't happen, but then I want to actually go fix that so that we no longer have to adjust the clip rect. All right, so the clip rect, right, here's our clip rect to do, correct buffers with overflow, right? So, okay, what I want to do here is just say, okay, let's make sure we have 4 pixels on all of the borders so that we can't possibly overwrite no matter how stupid our code is temporarily, right? Oops, didn't mean to actually do that to the one I was saving. So if I do that temporarily, hopefully I can avoid the crash, or we can just still crash, which would be cool. Do not know why I'd be getting that, because this should still give me, at least in theory, the correct, well, but it totally didn't. Why is my clip rect, did I set the clip rect wrong? Oh, wow. Yeah, someone's getting sleepy, and that someone is me. That's the one I wanted to set. So there we go, and now we're not in the dreaded super slow everything, right? So now that we're passing the clip rect down, and that's all good, everyone's happy. What I want to do is make it so that render group to output is actually some totally other thing, right? I actually want it to look like this, where render group to output, get rid of all this stuff. Actually, you know what, though? I do want to still time this one, I think. So what I'm actually going to do, I guess, is make this be tiled render group to output or something like that. And I'm not going to time it. OK. Yeah, and we'll see. I don't know how we're going to actually line this up. Eventually, that's what we'll start looking at on Monday. But in here, where we do render group to output, oops, I actually want handmade.cpp, which I guess it doesn't want to give me. Give me handmade.cpp. There we go. So render group to output, I'm going to just call tiled render group to output now. We're going to have to do something a little fancier there, but that'll be next week's job. All right, so when we do our tiled render group to output, what this is going to do is I'm going to pass the clip rect in, like so, right? And then I'm going to pass in also, in addition to that, the even odd, right? So in here, this will now pass the even odd. All right, so we do that, and everyone's happy, and everything's good. And then I just go ahead and grab this out and put it in the outside thing. So tiled group, we'll just do render group to output, like so. Render group, output target, clip rect, false, and true. OK. And now we can just do one of these, because we're calling it twice, right? And off we go. Or not, as the case may be. What happened there? We're calling it twice. Begin time block bool even. Draw quickly, clip rect even, which is passing both. And we call it twice, once with each. Why am I not seeing the proper thing here? I would like to know. All right. Let's see what happens. So we should get no update to the frame buffer here, meaning I won't see anything if I try to move. This should give me one set of lines. This should give me the other set of lines, which it does. Oh, well, yeah. That's another thing we would need to do, isn't it? So right now, our clear call, right? Our clear call is actually just doing a draw rectangle, and that draw rectangle call does not in any way obey the even odd lines, right? So what we need to do is we need to update our draw rectangle call to take, you know, the clipping information, right? And that will allow us also, I suppose, to start clipping the rest of these things, which we want to do. So that's fine. All right, so let's go ahead and do that to draw a rectangle. So rectangle 2i, clip rect, bool 32 even. And this is probably pretty straightforward, I would think. It looks like these are just doing the clip here, right? So basically, this is just the fill rect, right? This is rectangle 2i fill rect, and this is just gonna do that, right? That's the fill rect, so then we can just do fill rect equals intersect, fill rect and clip rect. Get rid of this stuff. Then we just go ahead and use the fill rect here. Like so. And off it goes. Right? I feel like that should do it. Draw rectangle outline. Who calls draw rectangle outline? What? What? Does this even exist anymore? It doesn't. It doesn't, does it? All right. Let's get rid of this guy, so we don't care about him. Not even used anymore. Probably delete that case entirely. And draw rectangle, translate initialize, test diffuse. All right, so this guy is some kind of clear, we're sort of cheating and using the renderer directly out from underneath itself. That'll probably have to go away at some point relatively soon because we won't be allowed to do stuff quite like that anymore. But, all right, so if we did want to do that, we would have to pass it more information. I'm just gonna go ahead and nuke this test diffuse, test normal guys, I think, for now. Well, let's see. Where is it actually used? All right, so I'll nuke this guy for now, but just that guy. We'll just do that with, what was he was just passing gray, basically. So all we really need to do here is we need to do something where we'd actually fill him with gray. To do basically refill this guy with gray. Okay, we'll leave that like that for now. Okay, so let's get back to what we were doing. So now we have this guy, we have the draw rectangle call taking those parameters, but we're not actually using the even odd guy, the even odd part of it, which we need to do. So if we take a look at draw rectangle quickly, you can see that we've got the even there, and we need to do this operation, right? And we could actually make this operation be something that is common between the two routines, since they're so similar, right? Like you can see the way that this works up here when I do the fill, you know, draw rectangle. Where's the other guy? Where's my draw rectangle? Oops. Okay. So if I come over here and look at draw rectangle, you can see that essentially I'm doing the exact same thing, and I would be doing the exact same thing here, right? And so I don't know if maybe we want to make that be something, you know, that's more standardized. It's a pretty trivial piece of code, but you know, you never know. So now I think we are properly doing every other line. Looks like we've got Oh, because that's still in the buffer. So it looks like we're properly doing every other line in those calls now. So let's take a look and see. There, go ahead and fix that. So we're doing both. And there we go. So that looks pretty good, I think. Feels okay, I would say. Not too bad. So all right. So now we've got that working. And so then the last thing that I kind of want to do now is I'd like to get it so that we can do our tiles. And so what I'd like to do is do something like this. So let's go ahead and do a for I loop where we do tile x. Tile x is less than some number of tiles. Tile count x. Tile x plus plus. And in here, we will do a loop over both tiles. And inside each of those, we will do this whole operation, like so. And so now what I'm going to do is I'm just going to break the screen up into those pieces that we talked about and render each one separately. So what I'd like to do is say, okay, we've got a tile count x and we've got a tile count y. And those are how many tiles we want across and how many tiles we want down. Right? So what I want to do is I want to set that number to something relatively reasonable. Like I think we said before, 6 or something was good. Something like that. So maybe something like 6 by 4 or something. I don't know. 1080 divided by 2 is 540. 540 divided by 4 seems maybe about right. 1920 divided by 2. 960 divided by 6. Something like that. I don't know. Just throwing it out there. So there'd be 24 tiles that we've broken up into. Maybe that's a few too many. It's hard to say. Maybe we want more of like a 5 or a 4 by 4, so there'd be 16 of them. So let's take a look at what that would be. That'd be more like 256. 1080 divided by 2. So that's, 540 divided by 4. 135. So yeah, I don't know about that. That's really hard to say. Again, that's going to be caching. We'll have to tweak it, but let's go ahead and see. So if those are our tile counts that we're looping over, then we would basically just need to know how big each tile was, in each case. And I guess we don't, since we're not aligned, we don't really have any restrictions on what the tile widths actually are, because it won't actually affect how we blit to them. Now we might want them to be aligned to 4 anyway, just because that way, if you happen to be blitting something that covers the whole tile, you wouldn't pay the price on both sides. But do KC round to 4. But basically what we want to do here is just figure out how big the tile width needs to be. So we can go ahead and do those divides. Output height divided by tile count y. And that's how many we need to do there. And of course, we need our tiles. We need the tiles to actually fill the whole space, so they might overflow slightly. Right now, we'll undercut it. And we'll figure out what we want to do about that later. All right, so we'll do to make sure that allocator allocates enough space so we can round these or whatever. We'll figure out how we want to do that exactly. So we get our tiles in. Then all we have to do is say, okay, our clip rect is actually going to be the min x will be the tile x times the tile width, and the clip and the max x obviously will just be whatever the min x is plus the tile width, and the same will be true for the y. Right, here goes the y. And there we go. So if that is what we're going to do for the clip rect, which is now done, then I can adjust it by those sort of 4 values here and be done. And that will now give me little guys who they should have like on the screen a little blockade, if you will. Although that does not look what I would have expected. I don't really understand what's going on there with the clip rect. Still got a bug. I'll stand up for a second. My legs are tired. Tired legs. Tired legs. All right. So if we do the tiled render group to output here, we're passing in the clip rect, and we're getting some weird behavior there. So I've got the clip rect tile x, tile width -4. So those are the things we're supposed to be clipping to, and I don't quite understand why we're getting that look that we just got. So like basically oh no, wait, that's totally correct. Those are the ground patches, which are getting tile rendered basically, which is kind of funny, but that's just how that is. So there we go. So there's our tiled renders, and we can see the tiles because I subtracted 4 from them. And so I think we're pretty close to correct there. I don't know why. We have to go look at why those ground tiles do that weird disappearing thing. But those are kind of a thing that are separate on our list anyway. But if we take a look at what's going on there, I think we're pretty much good to go. So I think we can finally end the stream. We've done all the stuff I wanted to do for tiled rendering, so that's good. And we can look at the rest of it starting next week. All right, so let's do the Q&A here at midnight. Because I want to go stretch my legs. My poor left leg, my GIMP leg. I wish medical science was smart enough to fix my left leg, but it's not. Your top and right clip is off by 1. Top and right clip. So you're talking about all right. Well, actually, I gotta take a look on here. So the top and right clip is off by 1, which is, you're talking about in here, right? Is that what we're talking about? You're talking about the intersection code? Not sure what you exactly mean by top and right clip, but I'm going to assume that's true. So let's see. Well, I guess the other problem is here, I'm not sure what you mean by off by 1. Are you trying to say that there's a calculation that should be aligned, like that's being too conservative and it's filling 1 extra or 1 too few pixels? So it's either not always conservative, but it's filling 1 too many or 1 too few pixels in the region to consider? Or are you saying that something based on the clip that should be adjusted is being adjusted wrong? I'm not sure which one of those you're saying, unfortunately. Let's see if I can figure it out. So the inverted infinity rectangle, we come through here, and this is just taking the total size. I assume you don't mean anything in here because you said clip, which is, this is not the clip, this is the clip. So when it does the intersection, we've got the fill rect and we've got the clip rect, and we just want to know whichever one of those is going to be greater, right? So that, I don't understand exactly why that wouldn't be this value. Can you be more specific about that, potentially? Mol-Low EPI 32 is an SSE4 intrinsic. Ah, really? That's too bad. Molo. That's too bad. Because I don't really want to use those. Mol-Low. EPI 32. Yep. It sure is. Well, the good news here is that really everything would work fine with a 16-bit multiply, probably, if we just clip out the top, because the fetch y for x is going to be so the texture pitch, right? I assume we can keep all the texture pitches less than 64,000, because how big would that be, right? Let's think about this. So 65536, or 5 I should say, 65536 divided by 4, that's a 16,000 wide texture, so that's not going to happen, right? So the fetch y for x, that value is just going to be whatever the also proportional to, it's just going to be whatever the height of the texture is. So I feel like, you know, if the total texture size was always going to be, well, no, that could still exceed it. Yeah, that's unfortunate. That is unfortunate. I'm not sure what the best way would be to make that work. I mean, I guess you could do a mol-low and a mol-high. Like, you could try to recombine the two, because you know that each one of them is going to be 16. So I suppose you could do it that way, but at that point I do wonder if maybe this was just a stupid idea, because then you're probably introducing too many extra instructions, and maybe you would just rather have done it in scalar to begin with, right? And I don't know if that's true or not. But you see what I'm saying, right? You could do something where you're just like, okay, yeah, we've got, you know, we've got a mol-low and a mol-high of the 16-bit values that are in here, and then we try to reconstruct them. We try to reconstruct those by ORing them together and shifting up, you know, the other guy SSLI, EPI 32. We try to shift up the other guy by 16 and OR them together. Like recreate a multiply, right? So we could do it that way, but unfortunately it's a little more expensive. But I guess that's just what we'd have to do to stay in there. So you saw what I did there, right? All I was doing there was I needed to do a 32-bit multiply, but there is no 32-bit multiply in SSE2. So what I did is I just did two 16-bit multiplies and asked for the low and the high bits of the result and just combined them together to make a 32-bit value. That's all I did, because I knew that the two values that I was multiplying were both only 16 bits, but when you multiply them together, then they're greater than 16 bits. So, yeah. Will you revert yesterday's code changes where you changed by linear pixel unpacking code from floatmul to intmul? It was faster with floatmul. I don't know, because I'm not sure we're ready to do that yet. I think we should probably do that, but we might want to switch some other part of the loop to be 16-bit when we do that. So I'm not sure what we want to do there yet. I wanted to try and do the memory stuff first. How many more marathon streams will we have? They will not be often, but sometimes if I'm in the mood and I happen to be like, I know that like I don't have any plans for the day, and I'm not gonna be hanging out with anyone or whatever, I can throw one in. You should give a big thanks to Rigorous for sticking around and tried to give you tips knowing full well that you wouldn't see them in the chat. Of course I give a big thanks to Rigorous. We always give a big thanks to him. Would it be better to have tile sizes always divisible by 4 horizontally? Then there would be no need to deal with alignment and masking. Unfortunately, no, that's not true, right? So the reason that we have to do the masking is actually because we are unaligned when we're writing to the tiles. So even if the tiles were aligned, we're writing 4 pixels based on the texture itself, right? So, I don't know that there's a way for us to, maybe I'm missing something, but I don't know how we can fix that part by aligning the tiles, because we're not aligned to the tiles ever anyway. Does that make sense? I don't know if that makes some sense. Clip 1 too few pixels. Look at the edge of the screen. Look at the edge of the screen. You're talking about out here? I'm not sure. Now keep in mind we've got like well, okay. I'm not sure exactly what you're talking about. So we'll start with that. But we also have some annoying things here that I just want to point out. So we're not really at the point where we've gotten down to like looking at some of the robustness things. So, I realize that there's some weirdness here. But push rect outline. So there's a bunch of things that get outlined right now. And in fact, maybe if I turn that off for a second, it'll be clearer, just so we make sure we're all talking about the same thing. So if I turn off push rect outline, which is here. So if we turn off push rect outline, now we can take a better look at what's going on. Do you still think there is an off by 1 error looking at what we're looking at now? And maybe you do, maybe you don't, but I just want to make sure we're all thinking about the same thing before we go looking for that. If that makes sense. Just pretty sure I saw glitchiness off by pixel stuff near the edges, but it might have been recording. So, okay, well, let's see. Because I'm just wondering, like, we were drawing a rectangle outline there, which is was for a separate thing, which was the sim region, and this is just like too many things that kind of get piled on as we're sort of doing this because, you know, 1 hour a night, I gotta cut some slack sometimes, and I don't always go back and like pull out code and put it in a way that I can turn it on and off and stuff like that. So there's always like debug code kind of crufting up things. And so what you may have been looking at is the fact that there was a rectangle outlining just the edge of the screen that if we don't pull the camera back to show our regions in the debug camera mode, it draws like right at the edge. But the draw rectangle code is not subpixel accurate yet, right? We still are using the way old one that we wrote at the very beginning of the stream that just, you know, fully just rounds. And so you may have seen it kind of coming in and out over here. I'm guessing that might have been it. But I could be wrong. But yeah. So I don't know, you know, we can do it, we can look at this as well, right? And like I said, you know, there may very well be a problem still. That's totally on the table. But I just wanted to make sure that we're all looking at it fairly because other people may not have remembered. Well, and Fabian probably never saw that stream, so he doesn't even know that we were drawing that, you know? So yeah. Tile size mod 4, not masking for textures, but clip mask variable. Yes, I'm sorry. Martins, I'm just not sure exactly what you're talking about there. So the thing that I don't understand about the suggestion, I'll go ahead and turn these guys back on. The thing that I don't really understand about the suggestion that you're saying is that the clip mask variable has nothing to do with the tile size, right? I'm sorry, with the tile alignment. It has to do with where the fill rect is relative to the tile. Because we write unaligned, our fill routine aligns with the texture, not with the tile. And so no matter what the alignment of the tile is, it's still going to have to clip either the front or the back. Because the texture, the fill region is a certain width, right? And that fill width is not aligned to 4. So no matter what we do, we have to do that backing up, right? Either on the front or the back. So I just don't understand how aligning the tile would ever get you out of the business of still having to not draw those pixels, because it doesn't have anything to do with what the alignment of the tile is. It's the alignment of the texture of the fill region. That's what's causing the clip. Does that make sense? And Martins, yes, I understand why you're not thinking clearly so late, because I am not thinking clearly so late either. It's time for bed, certainly. Yes, it's pretty much 1 hour a day, but I think we've had a 2-hour one before, two 2-hour ones before, and today we did basically a giant 4-hour one. It was crazy. Like I said, I hadn't had enough programming. I had to do a bunch of talk prep at a conference on Friday. So, you know. And you can see it's 12:27 a.m. here. Time for me to go to bed. All right, folks. Good work today, though. We got a bunch of stuff resolved. So that's pretty good. And now that we've got tiled stuff in, we can go ahead and do multi-threading next week. That'll be pretty fun, I think. And then we can start working on renderer correctness and stuff. Get the lighting going. Get our whatever our fill rule is ironed out. Yeah. This is going to be good. The renderer is the biggest part of the engine, really, in terms of stuff that's kind of fiddly and stuff we have to work through in the way that we're working through with like optimizations and all that stuff that are really sensitive because there's just so many pixels that you deal with. So, I think we've done it pretty well. I think we've managed it pretty well. Obviously, not everything goes perfectly, but it's gone pretty well. I'm pretty happy with that. Even having chunk it up into an hour a night, we were able to make pretty good progress. We've got a renderer now that's pretty good. I mean, it's not going to win any awards for world's best renderer or anything, but it's totally at working at speed, and we'll be able to get it multi-threaded soon, and that's I don't know. I'm pretty happy with that. It supports scaling and rotation already. So we'll have to take a little bit look at what we can do with the lighting stuff, which is obviously worse and much slower. So I don't know how much of that lighting stuff we'll be able to do in the software path necessarily, but we'll think about it a little later on after we have the whole thing working well without the lighting. We'll go ahead and get all that good, and then we'll switch on the lighting stuff and see what we can do there. And that might take a little while too, but it's good stuff. All right, so thanks everyone for joining me for another episode of Handmade Hero. It has been a pleasure coding with you as always, and it has been a marathon session today, our first real marathon session. We've never gone anything like 4 hours before, so that was kind of fun. Just, it's good to work on the code sometimes for a little bit longer. And I never got a chance to do that before. As always, if you would like to follow along the source code at home, the game comes with the source code, so if you pre-order it at any time, you get all the source code to every day that we've ever done. And you can always download it every night if you want the latest. It's always up there. So you can do that on handmadehero.org using the pre-order now button. If you would like, you can also support our Patreon page, which is basically just supports the video, which of course we do as a free thing. But if you want to support it, we love that you do. And we also have a forum site you can go to ask questions, get ports to Mac and Linux or any other stuff like that. We've got a tweet bot that tweets the schedule at you. And we have a little, we're working on this. It's not really there yet, but there's some JavaScript that someone sent in that I put in that sort of works sometimes to set this properly. And hopefully when I get a chance, I will go clean up the JavaScript so that it always gets the right thing. So hopefully eventually this live button will also tell you how long it is to the next live stream too. So that's coming, but it's going to be a while till I have a chance to go look at it myself. So anyway, thanks everyone for joining me. Next stream will be Monday, back to the regular schedule. It will not be a marathon, just a regular 1 hour stream. And I hope to see you all there. Until then, have a fabulous rest of your weekend and have fun programming.